Hello everyone and welcome back to the channel. So you might be preparing for your certification or an upcoming interview, or you might be looking forward to a complete refresher on all the AWS databases. So if yes, then this video is for you. So today we are going to talk about all the AWS databases. I haven't included migration tools because we will cover them in a separate section like AWS DMS and AWS Glue. So sit back, relax, grab a cup of coffee because we have a lot to discuss today. And before moving forward, I just want to make sure that I make a request to you that these videos take a lot of time to make. So please make sure that you support my work by subscribing to the channel and giving the video a big thumbs up. So if you are ready, let's begin. So let's start off with the first database that we have here, which is QLDB, that is Quantum Ledger Database. So before we can understand what is a QLDB, we need to understand what is a ledger database and how does it work. So if you know, and you see here that QLDB stands for Quantum Ledger Database. So we must understand what is the ledger database and how does it work. So we can read the statement here. QLDBs are systems of record, supply chain, registrations, and banking transactions. So when you look at these terms, you should understand that it is a heavyweight database that needs the highest level of accuracy and audit. But I won't confuse you here by talking random stuff just like that. So just keep this statement in mind and let's move on. So the name of the database is Quantum Ledger Database. Leave the quantum part for now. Let's talk about ledger. So a ledger is a book or collection of accounts in which account transactions are recorded. So ledgers are typically used to record a history of economics and financial activity in an organization. So think of a ledger as a record. Imagine a banking scenario where people make a lot of transactions. So in a transaction, there might be multiple parties involved who have an account in the bank. There are millions and millions of transactions that take place within a very short time. But with these many transactions, there will be a few concerns. Like how safe are your transactions? How safe are your records? How fast can you keep track of the transactions? And what happens if the data gets deleted? How are you going to track it? And that is why you need a robust database solution, and that's why ledger is the talking point here. So that is why we need to talk about a database that can help us with this scenario. And that's where we need to talk about QLDB, that is Quantum Ledger Database. So let's see how good is QLDB. So Amazon QLDB is a fully managed ledger database that provides a transparent, immutable, and cryptographically verifiable transaction log owned by a central trusted authority. And you must be thinking, okay, it's transparent, so it means that we can audit and find the sequence of the transaction and its history. And it is immutable, so it means that the data that you have on the database cannot be changed. And cryptographically verifiable would mean that we might be using a hashing algorithm to verify each transaction. And if you're thinking on these lines, then you are 90% correct here. And we will get to this, don't worry. But it's not that we are only going to use QLDB for banking transactions. Ledger databases serve a lot of data. So it could be your banking transaction, it could be your insurance, it could be huge manufacturing inventory, it could be finances, it could be a simple car seller portal also. I know most of you might be thinking why this word quantum is being used here. So let's read this statement here. So a transaction can be in one of many possible states. Which one is unknown until fixed by observation. So one of the many possible states that we have for a transaction is only known when it is fixed by observation. And that is what we will find out today. And once we are done with the session on QLDB, you will have the answer to this. So the most important point that you need to understand is that companies build applications like ledger-like functionality because they want to maintain an accurate history of their application's data. So let's suppose you're providing, or let's suppose you're provisioning credit card and debit cards, or if you are giving loans to firms and you have a huge record of data that needs to be preserved accurately. So if you want to imagine all the use cases of where ledger can be used, just think of scenarios where you want to preserve the sequence of the data that has been stored. So if we take the example of supply chain, a supply chain has multiple stages, isn't it? Like procurement, manufacturing, warehouse, and transport, and all these are stages of the product flow and anyone who tampers with the state of the data at any of these stages might lead to a bigger problem. So there might be a counter argument of using relational databases, but data is way easier to manipulate and it is prone to human errors in relational databases. Because if someone pushes the incorrect transaction, and yes, there is a provision to roll back, but in a huge transactional scenario, that could lead to errors which would not be traceable. And that is why it is rightly mentioned here, relational databases are not inherently immutable, and any unintended changes to the data are hard to track and verify. And some of you might say that, hey, we can use blockchains as well. So yes, of course, we can make use of blockchains as ledgers, but wouldn't it be too costly and complex to set up? Yes, that's why let's just keep ourselves to QLDB for now. And that is why with QLDB, it is more feasible to handle this situation, because with QLDB, your data change history is immutable. So be assured that it cannot be altered or deleted. And in order to verify the data modification and change verification, QLDB uses cryptography to ensure that the data changes are being tracked even if they are modified. So QLDB also makes use of journal, which we will discuss in a bit, which helps it to have an immutable transaction log. It also has the streaming capability for a near real-time flow of your data stored within QLDB so that it can be used with other services. When it comes to deployment headaches, you don't need to worry about this as well, as QLDB is serverless and it automatically scales as per your requirement. And as with other AWS services here as well, with QLDB, you pay only for what you use. So that's something wonderful, isn't it? So this is a simple explanation about QLDB, but I just mentioned the journal, isn't it? So let's talk about what a journal is with respect to QLDB. So when we think of a journal in our daily life, it is like a record or daily record of news and events of a personal nature. So this is to keep track of the events, and if you see, there is a sequence to this. So every event that gets registered is sequentially updated on the journal, and that is what you need to keep in mind. So day 1, I drove my bike after 12 days. Day 2, I gave 1500 rupees, and day 3, I lent 500 more. Day 4, I went out for shopping for 2000. Day 5, I went for a drive that cost me around 5000. I got back 200 that I had given someone, and on day 7, David had asked me to meet him. So it is like a record for all the events that take place in my life, but it is of a sequential nature, and all of them can be recorded and can be backtracked to what the event was based on the day it was entered into the journal. So if this journal has your data, then can we say that a journal is a database? Let's check that out. So when you are working with databases, you add entries, isn't it? So let's say each change, whatever it is in your CRUD operation as a transaction, and that is what helps you to maintain the ACID properties. So your transactions are the core of your database operations, isn't it? And this immutable transaction log that you have on QLDB is called the journal. So I know you might have many doubts on ledgers and journals, so keep watching and let's talk more about this. So one thing you should have, or one thing you should always keep in mind, that the history of changes to your data on QLDB is immutable, which means it cannot be altered, updated, or deleted. So how do we achieve this using the journal or ledger? So in QLDB, when you write the data or perform the operation, it is append only, and every block of data that you have is a sequence of hash chained sets of blocks. I'll repeat that once again. It is append only, and every block of data that you have is a sequence of hash chained sets of blocks. So you might be thinking, what is a hash chained set? Don't worry, we will talk about that. So this is your client, and the application that you have connects to the ledger to run the transaction like insert, update, or delete. So let's add the first transaction of insert for phones. So here we have stored ID, product model, reference number and owner, and the metadata of date and time when the transaction took place, which is written in sequence to the journal, that is J here. So J denotes the journal here. And next what happens here is that the data is captured, or in database term materialized into the table with view, by which you can query the current state of the transaction. That is represented by C here. That is C here, which represents the current state of the transaction. This also appears to be captured as a part of the historical transaction, that is represented by H here. So historical transaction is represented by H. Let's add another update transaction. So where we are changing the owner's name of the product from Sam to Josh Doe. So here you can see in the historical table, we have a column called version with a version number. Now, if you see, the current state changes and has changed, and the history has added a new entry with a new version number. And each transaction is a sequence here. Transactions are committed to the journal as blocks that are hash changed for verification. Let's add the last entry here where we have a delete operation. So here if you see, the current state before delete remains the same, but the history has been updated with version 3 for the deleted entry. This is how the ledger keeps track of changes, and you can create journals to keep track of your transactions. And by using streams, we can send each revision in real time to Amazon Kinesis data streams for further processing. But you must be thinking, okay, we have the logs that are secure and sequential, but what exactly is that which makes it immutable? So let's check that out. So the first thing that you need to always remember is that there are no APIs or other methods to alter any committed data in place. So if you can't alter the data, then it is obvious that you can query the full history of the ledger. So that's a very important point. So there are no APIs or methods to alter any committed data in place in QLDB. So if you can't alter the data, then it is obvious that you can query the full history of the ledger. So each block that you have here represents the operation object that your data is about, like insert, update, and delete. So in order to protect the overall accuracy, completeness, and consistency of data, we have to sequence them and chain hash them so that we can verify the authenticity of the data. So here each block has a sequence which also acts like an address for the sequence for every transaction, and there is a hash chain like this: 310, 311, 312, 313, 314. And this is a sequence number. Whenever you make any operation, it gets appended to that. Okay, so a lot has been said about hash chaining. Let's see what it is about. So we already know that journal blocks are sequential with a sequence number and are chain hashed together with a cryptographic hashing technique. So yes, similar to the blockchain technique, I know. So here we are using SHA-256 hashing to generate the digest or hash value in such a way that every step of time you can validate the digest to ensure that your data is verified and is authentic. So if we expand a block, you can see the actual components present in the block. So here you have the data, the metadata of your data entry, and the particle statement that you have executed for the transaction processing. And here Amazon QLDB supports a subset of the particle query language by which you can create your transactions. So Amazon Ion document that you see here is an abstract data model that lets you store both structured and unstructured data and is a superset of JSON. So superset in the sense, if you have a valid JSON document, it can also be called as an Amazon Ion document. So it's simple as that. And along with these three, you have a block hash that you see. And I'm sure you might be aware of how encryption or hash functions work. So we won't go much deep into that. You can check out my videos on KMS that has some details on this. But I am not still satisfied of how this block works or how the hash chaining works. So let's dig more deep into this. I'm sure you also want to. And before moving forward, I just want to reiterate that we are using SHA-56 hashing to generate the digest or hash value in such a way that every step of time you can validate the digest to ensure your data is verified and is authentic. So now we are good to go. So as I've already mentioned before, the integrity of the data is its accuracy and consistency over its life cycle, like when it was inserted or when it was updated, and finally when it gets deleted. So throughout its life cycle. And you know that a ledger has a journal, and in that you have your immutable transaction logs, which we discussed a few minutes back. And this immutability aspect of the transaction logs and this statement holds true under these two conditions. The first condition is it exists at the same location in your journal where it was first written, based on the document revision history that you have, that you can translate to, and it hasn't been altered in any way since it was written. So it doesn't mean that it should be updated. It's about the data altercation also. So these two statements are the underlying conditions where the statement actually holds true, where we say that we have the immutable transaction logs. So please keep in mind these two statements. That first statement is it exists at the same location in your journal when it was first written. And the second one is it hasn't been altered in any way since it was written. Okay, so the position and the data that it has should be authentic and the integrity of the data should not be altered. And when we talk about data integrity, there are four basic components of verification. So the first one is hashing, the second one is digest, the third one is Merkle tree, and the last one is proof. We will discuss them one by one. So when it comes to hashing, you have to understand in cryptography, when you're using a hashing function algorithm, here we are using SHA-256, as I already told you, which produces a 256-bit 32-byte hash value, hexadecimal number of 64 digits. So the value that the hash function returns is the hash value, or it is also called as the digest, that is the output that you generate. So in the first step, we create the hash value with a fixed size using the SHA-256 hash function. And even if you change a single digit, the hash value changes. That is what you see in the second step. So if we change the name of owner from Sam to Josh Doe, the hash value also changes. But you have to understand that you can convert an input to hash value, but it's not the other way around. So if you have an output, it's not mathematically feasible or possible to compute the input when you provide an output. Yes, seriously, you cannot. It's not mathematically feasible to compute the input when given an output. Now let's talk about what is a message digest. So a message digest is a fixed size numeric representation of a content of the message computed by a hash function. So it's simple as that. So it is a fixed size numeric representation of the contents of a message computed by a hash function. So which we just discussed now. And message digest can be encrypted, forming a digital signature which will be used to validate the authenticity and integrity of a message. So let's bring the input, that is the data that you have, and then by using a hash function like SHA-256, we can create the hash value. So if the input is 123.112.123, by using a SHA-256 hashing algorithm, I can compute the cryptographic value for that one, and that will be my message digest. So I hope you got this. Now let's understand how do we actually verify the data integrity using Merkle proofs. So before understanding Merkle audit proof, let's go through a very important concept, that is of hash chaining. We all by now understand that hash chaining is used for cryptographic verification of the integrity of the data. So let's suppose this is your data, or this is our data, and its sequence is A, B, C, and D. Next, when we use our hashing to create our hash chain, that is, it becomes H of A, H of B, H of C, and H of D. To keep it secure, we can create a root hash by combining all these hash values. Let's see. So this is how we are combining all the hash values and creating a root hash. And then by using the hash function, we create the root hash and store it on our trusted servers. So once you have all the hash values, you can combine them and you can keep the root hash value, that is H of A, B, C, D, in the trusted server that you have. So next, if you want to verify this, so for a verification, you know that each hash value can collect the hash values of other blocks and compute its own hash and create a root hash and compare it with the one that is present on the trusted server to ensure the data that we have is valid. So this is the whole idea. So you create the root hash, and once you have created the root hash and you have stored it in your trusted server, you can compute the other blocks that you have for the root hash value by using one of the computed blocks, and you can compare the one that has already existed on the trusted server with the one that you have, and thus you can validate the data that you have. So this is a general idea. But what if the server gets compromised and you get a compromised response? So in a way, you will not find the root hash on the server. So how do we solve this problem? So is there a way for the server itself to prove that it has the correct data? So I'm asking you this question again. So is there a way for the server itself to prove that it has the correct data? Yes, there is. So here is our current setup, and now here what we can do is we can store the root hash along with the blocked hashes or the block hashes together on the trusted server. So this might be a costly affair, but we will eventually have the proof that the server has the correct data. So for its verification, what the server might tell you that I have all the block hashes, and by using these we can compute a node hash. So by using HA and HB, we can compute HAB. So by using HA and HB, I can compute HAB. By using HC and HD, I can compute HCD. And now we have the leaf nodes HAB and HCD. And then using these leaf nodes, we can compute the root hash, that is HABCD. So if this actually matches the one that you have, then your data is secure and you have the authentic data on your server. But if any of these values get changed, so if this becomes HA and HD, then you will not be able to compute HAB. And thus you will not be able to compute the root hash, that is HABCD, which is already present on the trusted server. So I hope you got the point here, and that's where we are ready to understand Merkle audit proof. So now we have reached a point where we need to understand Merkle audit proof. And if you're hearing this concept for the first time, don't worry, it's simple. You are already on your way to teach others what is Merkle audit proof. So let's read these lines that we have here. So a Merkle audit proof lets you verify that a specific certificate has been included in a log. And this is a critical verification task because the certificate transparency model demands that all TLS clients reject any certificate that do not show up in the certificate log. So I hope you read this carefully. So what it is trying to tell is that we have a certificate and we need proof that it is present in the certificate log. And if it is present, then we can say that this is a valid certificate. Else we can reject that certificate. So this Merkle audit proof is just a concept that helps us to identify whether the data that we have is authentic or not. So the process to find the proof is provided by the Merkle audit proof with the help of Merkle tree. Yes, so the process to find the proof is provided by the Merkle audit proof with the help of the Merkle tree. So I'm not sure if you understand Merkle tree, but that's what we are going to learn today. So don't worry. So what I want you to do is replace the certificate here to block, and you will get the answer on how Merkle audit proof is being applied in QLDB. So let's suppose this is our root hash, that is Merkle tree hash. As I told you, the example that I showed you before, just try to relate to that and try to replace the certificate here to block. And what I want you to do is replace the certificate, the word that you are thinking here right now, to block, and you will get the answer on how Merkle audit proof is being applied in QLDB. Okay, so let's suppose this is our root hash, that is the Merkle tree hash. Then we have the node hash. Then we have the leaf hash. And then we have the certificates. Okay, so the first thing that we have is the root hash. Then we have the node hash. Then we have the leaf hash, and then we have the certificates. So let's suppose you have a certificate D3 and you want to validate its authenticity from the trusted server. Okay, so that is what we are going to do. We are going to audit proof for this certificate. So you ask the server to provide the proof. So what the server does is that it sends the appropriate hashes as proofs. So it'll try to send you the proofs, but don't think now about what basis the server sends the proof. We'll discuss that. So here we have three nodes, I, C, and N. I, C, and N. So here we have three nodes, that is I, C, and N. And using these, we have to compute the root hash. And if we are able to do that, we can conclude that our audit trail is successful. So now that you have D and the server has given you C, what you can do is we can compute J by using CD. And as we know J and as we know I, we can compute M. And as we know M and N from the server, we can compute the root hash. And then we can compare the compute of H, D, C, J, I, M, N is equal to the root hash or not with the original root and validate it. Okay, so this is how Merkle audit proof actually works. So let's reiterate on this once again. So now that you know D, the server has given you C, so you can compute J. using C and D. And as we know already that we have I and J, then we can compute M. And as I already know N, I can compute the root hash, that is DCJIMN. And that will be my root hash. And then we can compare the compute of HDCJIMN with the original root and validate it. So if it is correct, then the certificate that you have is valid, else it is not valid. And now you know why QLDB is so popular, because it follows so many principles just to verify and make your data accurate for you. Okay, so now let's talk about Particle database. So the query language that QLDB prefers is Particle, which is like SQL, but this has been provisioned to work with ION documents. So let's see some of the similarities and differences between both relational and QLDB. So in your relational database, we have the database, the table, index, table row, and columns. And when it comes to QLDB, the database here is the ledger. We have the table view, we have the index, and the table row becomes Amazon ION document, which we actually provide as our data. And the column in relational database is document attribute here on QLDB, where it's the document ID to each document that we insert. So the query language for the relational database is SQL, and for QLDB is Particle, which is an open source SQL compatible query language to work with IONs. And the audit logs that you have on relational database are the journals here on QLDB, which we have already discussed before. So I hope you got the idea of the similarities and the differences here. Let's move on. Now let's quickly talk about the architecture, which you would have no doubts about understanding now. So you have your application data that gets connected to the QLDB, within which you have the current state and the historical data and the table view. And along with that, you have the immutable transaction log, that is the journals. From the current state, you can query for the complete history of the data that you have and the changes that have been made on the data itself. Similarly, using the journal, you can cryptographically verify the integrity of the revisions made on the data that you have. Simple, isn't it? Now let's talk about some of the benefits and recap on the things that we love about QLDB. So the first one is immutable and transparent. Every data that you push is stored as a block and is kept as a part of an immutable log, that is a journal. And that is what helps QLDB to maintain a complete and sequenced history of changes over time. Second one is cryptographically verifiable. For data integrity and verification, QLDB uses a cryptographic hash function, SHA-256 or SHA-256, to generate a secure output file of your data's change history known as the digest, which we already discussed, and remember this, it will be very important. So when it comes to performance and scalability, Amazon QLDB is highly scalable and can execute 2 to 3 times as many transactions as ledgers compared to the common blockchain frameworks. So this is because blockchains are decentralized, which means that you're not logically connected and they may not be on the same communication network. So to get the majority, it will take time. But QLDB is centralized, so you don't need a consensus or majority to agree for the transaction to take place. So it's faster than other blockchain techniques. Next one is serverless. So you don't have to worry about scaling or provisioning resources when your demand increases. So that's a good thing. And the other one is QLDB is highly available. So you get your data replicated within and across availability zones within the region for your data to be highly available, and that too without any additional cost. Moving on to the last one, ease of use or usage. So as we already discussed, QLDB supports Particle, a new open source SQL compatible query language designed to easily work with all data types and data structures. So why are they saying this is because considering the fact that Particle is SQL compatible, you will find it easier to mold yourself to use this, and it's based on Amazon ION, which is a subset of JSON. So it will be more familiar for the developers and the designers to use. So let's talk about some of the use cases of QLDB. So the first one is finance. So ledgers are very important or very much important when it comes to banking transactions, where the authenticity of transaction is the core. For example, a bank has various divisions like debit and credit and loan, and each transaction that takes place has to be tracked in a way that it can prevent it from being manipulated. So in finance, it can help the companies to have a better system in place. The second one is human resource. So when you talk to your HR, it's not just about the salary of the employee. There is more to what the HR department has to deal with in terms of data related to the employee. It might be payroll, the bonus, the benefits, performance history, insurance, exit formalities, enrollment, and all that is a set process. And QLDB can help retain and maintain data in a way that it provides conclusive evidence of the state of the employee at any given time. The third one is insurance. So as we know, insurance data is very complex, starting from the inception of taking the policy to having the historical data of the claims related to the insurance. More than that, insurance also deals with second or third party beneficiaries, which amount to a lot of data that has to be taken care of with respect to the life cycle. So here the cryptographic verification helps insurance companies to validate the data and its state at a given point of time. Next one is retail and supply chain. So retail and supply chain is a process-oriented business model which starts from inventory to sales to delivery and logistic. So QLDB helps supply chains to track down the historical data of the changes that take place in the process chain accurately. So the last one that we have here is manufacturing. So just like the supply chain here as well, manufacturing is somewhere you need a provision to track the progress and historical data of your production chain. So QLDB can help easily track the history of the entire production and distribution lifecycle of that product. So now you know why this is called as quantum ledger. So a transaction can be in one of many possible states. Which one is unknown until fixed by observation. So starting from the immutability aspect of the journal to the cryptographic validation of your data block, this is something that makes it easy for you to track the data and its state at a particular given point of time. And that is why the name is quantum. So this is where we end our discussion on the quantum ledger database. I hope you were clear with this. Let's move on. So now let's talk about a very interesting database, which is Amazon TimeStream, fast, scalable, serverless time series database. So how fast is it? And what is a time series database? So let's find out. So now let's talk about a very interesting database, which is Amazon TimeStream, fast, scalable, serverless time series database. So how fast is it? And what is a time series database? Let's find out. So before moving forward, let's design an application, our very own weather application, which shows us the temperature of cities at a given point of time. And it also shows what is the weather like for that particular time. So now to achieve this, we need the time and the data about what is the temperature and condition at that particular time. And for the UI, we need a graph that actually shows the time and temperature graph. So that's how we are going to denote what pointers we have. And at 8 a.m., as you can see, we have the temperature at 2 degrees and it will rain, obviously. And at 10 a.m., it will be around 12 degrees and there is a slight chance of rain. And 1 p.m., the temperature will be around 22 degrees and it's slightly windy. And similarly, we have 4 p.m. we have it around -2 degrees centigrade, and at 8 p.m. it is around 2 degrees. I don't know which city is having so much fluctuations in the temperature, but okay, not a problem. Similarly, we have other data. So this is a data set that we have. So temperature and the time. And what we understand here is that for our application to work, we need the data at a particular time so that we can represent that. And this data has to be accurate and shouldn't be manipulated. And we can also denote that it's a stream of data that comes in as an input, because it is going to change every day and every hour, every minute, every second. And here we can make use of a database that can help us achieve this or track this. And that's where a time series database comes in handy. And that's why a time series database contains data for each point of time. And this is not a new concept. We have a lot of time series databases that are already available to us, like InfluxDB, KDB+, Prometheus, and others. And there are a lot of variations to this as well. But we are here to discuss about time series or Amazon time series. So let's talk about this. So now let's see the architecture or the high level architecture when we use TimeStream. So we have the data, the real-time data, which we feed to the time series database. With the time series or time series database or TimeStream database, you have to understand three concepts. interpolation, approximation, and smoothing. So when it comes to interpolation, as per mathematics, interpolation is a type of estimation, a method of constructing or finding new data points based on the range of a discrete set of known data points. So what AWS tells us is that if your time stream data is missing values for certain events at certain point of time, you can estimate the values of those missing events using interpolation. Your time series database provides you the interpolation functions, and it also has around 4 variants like linear interpolation, cubic spline interpolation, last observation carried forward interpolation, that is LOCF, and constant interpolation. And here we are not going to discuss this in depth because it's too much information for you at this time. And when it comes to smoothing approximation, these are also techniques for time series forecasting where you predict the future data point based on the past values that you have. Mostly we do a weighted average of values based on the observation that we have. So these are some of the functions and algorithms used as a part of the time series database to provide you the data and its outcome, which can be used for analysis, prediction, and thus we get the data for our application. So Amazon TimeStream is a fast, scalable, fully managed, purpose-built time series database that makes it easy to store and analyze trillions of time series data points per day. So it's perfect for our application, isn't it? But wait, let's see what it can provide us for us to achieve the level of performance we need for our application. And for that, we need to understand a few core concepts related to the time series database. So the first one is time series. So this is basically a sequence of one or more data points or records recorded over a time interval, like our temperature and time data that we had, or it can be CPU or memory utilization of an EC2 instance over time. The second one is a record. That is basically a single data point in a time series. For example, at 8 p.m. temperature is 32 degrees. So it's a single data point. Third one is dimension, an attribute that describes the metadata of a time series. So this has dimension name and a dimension value. For example, if you have dimension is city, the dimension value is New York or Mumbai or Delhi. So the fourth one is measure. So the actual value being measured by the record, like what temperature it recorded, what was the weather. Here also we have measure name and measure value. So if suppose your measure name is humidity, then the measure value is actual humidity level, like what percentage is the humidity. The next one, or the fifth one, is timestamp. So indicates actually when a measure was collected for a given record, indicating the time at which it was collected. So it's a simple one. Sixth one is table. So a container for a set of related time series. It's like your collected data points, like your data table. And the last one is the database. So that is basically your top level containers for your tables. So these are some of the most important concepts or terms for us to remember in time series database. And whenever you're having a discussion about TimeStream with someone, then these pointers will be really helpful. So these are some of the important terms for us to remember in the time series database, that is Amazon TimeStream. And coming back to how TimeStream actually works, AWS has given a very good summary about how the TimeStream actually works. So we can discuss more about this. So in TimeStream, a database contains 0 or more tables. And each table contains 0 or more time series. I'll tell you how. So each time series consists of a sequence of records over a given time interval at a specific granularity. Each time series can be depicted using its metadata or dimension, its data or measure, and its timestamp. So these two that you see here are the series, and this is the record, which is a single data point in the time series or in a time series. So this is your record, and these two are the series. So you can see how it is being laid out here. Here in series 1, you see that we have the dimension city and the dimension value as New York. We have the measure name as temperature and the measure value as 32 and 23. And we have the timestamp, which indicates when a measure was collected for a given record, indicating the time it was collected. So now let's talk about some of the internal architecture for us to understand how it manages the time series data and its processing. So we all know that TimeStream has a serverless architecture, and here we have to collect the data, store it, and process it. So we have 3 states in the life cycle, and that's how we will analyze this. So the first stage that we have here is ingestion layer, which is also the write architecture. When you write the time series data to TimeStream database, we use the write APIs and SDKs to do that, obviously, isn't it? So this data is written to the ingestion layer, like we are ingesting the data on the ingestion layer, post which it is written to the memory storage layer. As it is serverless, you don't have to worry about, or you don't worry about the huge amount of data, as the data ingestion layer is designed to process trillions of events per second, and it scales horizontally to match the specific requirements of your application. So here, if you see, the incoming data is processed at the in-memory store, which cleans up the data like removing duplicates, and then it replicates it across 3 availability zones. Which brings us to the storage architecture, or the storage layer. So here in storage architecture, the most important thing is magnetic storage, which helps you to store your data based on the data retention policy. And here the data is being optimized for read queries so that it can be retrieved at a faster rate. So how does it work? So it works because when we push the data to a time stream, it is automatically indexed based on the attributes it has to ensure that it has the best performance oriented data retrieval when we query the data. So we have stored the data and processed it. So how do we retrieve it? That brings us to the query layer. That is the query architecture. So you might be thinking that itna sara data hai and it's coming into the TimeStream, and there'll be huge amount of data that has to be queried. So how does TimeStream handle this? So here in TimeStream, we have a purpose-built adaptive query engine. So I'll repeat this once again. So in TimeStream, we have a purpose-built adaptive query engine. So what does it do? So the querying is taken care by a dedicated fleet of workers. So fleet is like a group of ships moving together, or a group of vehicles moving together with a purpose or a goal. So here the dedicated fleet of workers, which are independent of the ingestion and the storage nodes that you see above, help in executing the queries. So you might say, if we query a large amount of data, so how it can handle this? So that's a very good question. So here what happens is TimeStream has a mechanism of massive parallelism between the query execution fleet and the storage fleet. And more so, the most important part for you to remember is the number of workers provisioned to run a given query is determined by the complexity of the query and the data size. So huge amount of data to query, the number of workers increases, but this is achieved with massive parallelism. And don't worry, TimeStream is also capable enough to access and combine data across storage tiers. So whichever you want, it can be queried. So whichever data you have, it can be queried. And it doesn't stop there. TimeStream also as well can provide you virtually infinite scaling, and that is done by using the cellular architecture. So what is cellular architecture? Let's talk about that. As I told you that memory storage process incoming data from the ingestion layer, removes extraneous data and replicates the data across 3 availability zones. But for this virtually infinite scaling, what TimeStream does is that it creates or segments multiple smaller copies of itself, which is also called as cells, and thus the name cellular architecture. And the best part is that you can have multiple cells per region, as we have 2 here in the single region shown in the image. And this ensures we have 99.99 availability, or 99.99% availability. You also might have doubts on how data will be ingested and read between cells. So here what happens is that you see the discovery endpoints. So TimeStream write and TimeStream query. The query requests are first processed by the discovery endpoint for both ingestion and query, and it redirects the request to the appropriate ingestion and query endpoints. And when you're working on this using APIs, as it will be transparently handled by the TimeStream, you will be never getting to know what exactly has happened, because it will be smoothly handled by the TimeStream database. So that's one of the very beautiful things here. So you have the TimeStream query and the TimeStream write discovery endpoints, and within that, within each cell, you have the cellular endpoints. And as it is transparently handled by the TimeStream database, you will have a great time using this. So I hope it was clear. Let's move on. Now let's discuss about some of the use cases of using TimeStream. Let's take the example of DevOps. So let's discuss the use case for DevOps and how it can help monitor health and usage metrics and analyze data in real time to improve performance and availability. So here you have the source of the time series data, And you can use Prometheus as your data collection agent, which gets stored and processed and can be used for monitoring the health and analyzing the data in real time. And here you can see we are making use of QuickSight to create dashboards. We can use it with AWS SageMaker, Grafana, or even we can store it in other forms of data querying structures using object models. And now it's time for us to talk about the most complex database in terms of the learning curve. Yes, let's talk about Amazon Redshift. So analyze all of your data with the fastest and most widely used cloud data warehouse. So if I have to say the database that you make use of for petabyte scale big data processing, that will be Redshift. And that should be enough for your exam as well. But should we stop it here? No, let's dig into this. But before moving forward to Redshift, we have to understand what is a data warehouse and why is it a complex system. But we won't go deep into this as this is a huge topic to cover, but at the end of this, you will have some idea if you're totally new to this. So what AWS tells us is that Redshift helps us to analyze all the data with the fastest and most widely used cloud data warehouse. So Redshift is a cloud data warehouse. So we all know what is a warehouse. So if suppose you are an online retailer like Flipkart or Amazon, and all these have different business units like manufacturing, packaging, logistic, and they also store a bulk of their products in a place that is used infrequently. So if suppose you get a consignment of 100 television sets, and out of the 100, 10 orders have been placed. Then the other 90 are placed in the warehouse. Similarly, you don't just have one product, you may have thousands of products, and each of the delivery comes to the warehouse for storage from different places, and all this gets stored here. And when we come back to the data warehouse, or when we talk about the data warehouse, it is not far away from what a real life warehouse is. So just like in a warehouse, we have boxes of different sizes and capabilities. Data that we have also is of different types and sizes. And the data warehouse acts as a system that collects all these data from a vast range of services and applications with the organization, and this data is also being used for numerous applications like KPI reporting, analytics, and also used for data mining. So in data warehousing, you take all the data from different sources, you compile and organize the data into one common data store. So I'll simplify this further. If you are new to data warehousing, just focus on this. So this is your data, which is collected from various sources like streams, database, flat files, relational databases, transactional data, multimedia, time series data, anything that you want. And then you transform it. So all the data that you collected is raw data, isn't it? So we need to clean it and then transform it to a form that can be consumed by other applications. Then we take the transformed data, and now it's time for us to load it to the target database for the application to use. So this is a simplified view of data warehousing with the ETL component, that is extract, transform, load. I hope you got the point here. Let's move on to a bit more complex architecture. The source of the data that you have can be from anywhere. It could be CRM, ERP, or transactional data that companies have in bulk. So imagine this to be in a finance enterprise. They have a lot of, they have a huge amount of data, the level at which you can't even imagine. To simplify this data, or for it to be consumable, we should transform that data. So let's suppose, imagine if you are the head of an organization and you want to view the KPI of your business units, you can't go to him and tell them that this is the database, you can query the data that you want. So he might just throw you out. So that's as simple as it can get. So most companies who deal with a huge bulk of data use this data for decision making, and this decision making depends on the collective data that you have. But that data, that raw data that we have, which comes from multiple sources, has to be cleaned and structured. And for that, we use ETL to transform it and store it in the data warehouse. And once you have segmented or segregated your data into lines of different units of business that you have, for example, you have finance, you have manufacturing, human resources, technology. So we can store that data respectively into these repositories, which are data marts. And yes, you can call data warehouse to be a collection of data marts. And then we use OLAP for the query processing using the data that we have. OLAP is online analytical processing, and most of the companies have multidimensional data. Like if I am Flipkart or Amazon, I have products like electronics, furniture, books, home decor, kitchen sets. And in that as well, you have different companies, like different price ranges, different countries, different colors. So OLAP organizes the data into a multidimensional format, and which can be used by teams for analytics, mining, and reporting. So I can talk more about the OLAP cube and how it helps to process and analyze the multidimensional data, but it is not needed here. And now let's talk about some of the advantages of the cloud data warehouse. When you make use of cloud data warehouse, you don't need to provision hardware and set up your own servers and databases, which could lead to provisioning cost and the additional overhead of maintenance. That's one of the good things. And the next advantage that we have here is it is easier to set up because you need to just launch your data warehouse by the desired configuration you need. So based on your requirement, you can set up your own data warehouse that is on cloud. And the biggest advantage that you have here is it scales up as per your requirement and the demand that you have. Faster and scales on demand. So now let's talk about the database clustering and architecture side of Redshift. So Amazon Redshift Data Warehouse is an enterprise class relational database query and management system. I'll repeat this once again. So Amazon Redshift Data Warehouse is an enterprise class relational database query and management system. And Redshift supports connections to a wide range of applications for reporting tools, analytical tools, or analytics tools, and BI as well. And the best thing about Redshift is that most companies have a good time migrating to Redshift, as Redshift is based on Postgres or PostgreSQL. So existing applications can work easily with Redshift. So the client application that you see here could be working on ETL, data mining, or analytics tools that can make use of Redshift for the data processing and storage. And AWS Redshift supports connection to database using JDBC and ODBC. They are very famous ones in the market. ODBC is if you're using Windows, as it's platform dependent, and JDBC is used widely because it works on multiple OS platforms. And the core of AWS Redshift is its Redshift cluster. On cloud, most of the times you'll hear this word cluster. This concept I feel is quite mostly used because when you want to have high performance, you launch compute nodes and connect them with high quality networks so that it works in tandem, and the cluster concept has been widely used for that. So here as well, when you have multiple compute nodes, we have a leader node that manages these nodes. So the communication that happens from the client is managed by the leader node, and then it propagates to the compute nodes. As the leader node acts as a master, the complex queries or complex operations will be managed by the leader node, and it does this by creating the execution plan on how it can execute complex queries, and then it compiles the code and sends it to the compute nodes. As the leader node acts as the master, the complex operations and queries will be managed by the leader node, and it does this by creating the execution plan on how it can execute complex queries, and then it compiles the code and sends it to the compute nodes. And you might ask me, what is compilation? So in Redshift, the leader node actually helps you with query compilation cache. So the question is, what if you are executing the same queries again and again, or what if you change a few parameters? But here we are not talking about simple select queries. So these queries that you see here can be bulk queries. So you should imagine at a scale for enterprise levels or large enterprises. It's not your student table database. So you must understand the gravity of the query that is being executed. And the way it gives the queries to compute nodes is by using query reference tables that are stored on the compute nodes. Else, apart from that, all the queries are executed on the leader node. So I want you to keep your eyes on the compute node that you have here, or that we have here. So the compute node that you see here have their own CPU, memory, and disks that you see, and the storage nodes that it has. And if you wish to scale, you can do that when your workload increases. So you're already aware of how scaling works. Here as well, it's the same. If you want to increase, you can increase compute capacity, storage, or number of compute nodes, and you can do that both to meet the demands that you have. As I already told you, the leader node actually compiles and sends the compile code to the compute nodes. The compute node take it and execute it. And then they send the intermediate results back to the leader node. And based on this, the aggregation takes place in the leader node. This word aggregation appears to be a very complex term, but in simple terms, it's just a combination of multiple entries that you have, and you combine them to get a meaningful data from that. It is just a simple way to put it. And if you see here in the compute nodes, there are a few bread slices, isn't it? So they are called node slices. So the compute nodes are partitioned into slices, and the resources that the compute node has is being shared with the slices so that they can carry out portion of your execution query. And best part is that the slices work in parallel, so you get better result and performance. And we have better communication with private high-speed network between leader nodes and the compute nodes, so you don't have to worry about that. And now you might be thinking, where is the database? So as I already told you, Redshift is based on PostgreSQL, and each cluster has one or more databases and works on RDBMS. And it also has OLTP features, but there are a few differences between the actual Postgres that you might use and the Redshift that you get to work on. So like on Redshift, you don't get the features like table partitioning, table spaces, constraints, unique, foreign key, primary key, and other important features like triggers is also not supported. So I would request you to please read more about the differences to have a better approach when you work with Redshift. So I hope you got the point here. If you felt you didn't understand a few pointers, you can rewatch this session. It really helps to revisit a section to get the best out of it. So let's summarize this once again. Amazon Redshift Data Warehouse is a collection of computing resources called nodes, which are organized into group called a cluster. Each cluster runs an Amazon Redshift engine and contains one or more databases. So leader node acts as a master. The complex queries and operations will be executed or managed by the leader nodes, and it does this by creating the execution plan on how it can execute complex queries, and it then compiles the code and then sends it to the compute nodes. So the compute nodes here takes the query and executes it and then sends the intermediate results back to the leader node. And based on this, the aggregation takes place in the leader node, and that's how you get the result. So the next thing that you should know about is how performance is taken care of in AWS Redshift. The first thing that we have here is massive parallel processing. So massive parallel processing MPP enables fast execution of the most complex queries operating on large amount of data. As I already told you, the Redshift cluster along with the leader node has multiple compute nodes which handles all the query processing and sends it back to the leader node for final result aggregation. And as compute nodes are partitioned into slices, with each slice of each node executing the same compiled query segments on portions of the entire data. So this way they execute them parallelly and give you the better performance. Second one is columnar storage. So columnar storage for database table drastically reduces the overall disk IO requirements and is an important factor in optimizing analytic query performance. When you have columnar storage, you tend to load very less data onto the memory, which in turn helps Redshift to have a better in-memory processing performance when executing queries. So don't worry, we will discuss this in a bit now, so keep watching. The third one is data compression, and data compression reduces storage requirements, thereby reducing disk IO, which improves query performance. As I already told you, loading fewer data into memory enables Amazon Redshift to enhance performance in memory processing. The data also is being compressed and then stored into the memory, and it is uncompressed when we are actually executing it. So in Redshift, you also have automatic compression with table loading, so that's something to look into. The fourth one is query optimizer. So the Amazon Redshift query execution engine incorporates a query optimizer that is MPP aware or massively parallel processing aware, and also takes advantage of columnar oriented data storage. When you work with Redshift, mostly you will work with DML, that is data manipulation language, which is a subset of SQL. So mostly it is about view, add, change, delete data. So it's more like select, insert, update, delete the transaction that take place. So this means that retrieving and viewing data is a core of what we work with when it comes to Redshift. And for query optimization, it's not that only Redshift works any magic into this, but this also depends on how you design your tables effectively, and you can read more about them on how you can design your queries or tables effectively in the documentation. And it also depends on leader node query processing, and we will discuss this. So I'm keeping this short for now. The fifth one is result caching. So to reduce query execution time and improve system performance, Amazon Redshift caches the results of certain type of queries in memory on the leader node. In Redshift, result caching is enabled by default, which you can disable by setting the enable _result_cache for session parameter to off. So the parameter that we have is enable result cache for session, and that you can set to off to disable this. So here as well, not all results are cached, and it depends on what is the size of the result itself, the query result, what is the size of the instance of the Redshift cluster, and also the number of entries in the cache as well. So eventually it does not cache all the results. So it will depend on what is the size of the query result, what is the size of the instance of the Redshift cluster, and also the number of entries in the cache as well. So when you submit a query, the leader node actually checks if there is a result in the cache, and if the result already is present, then it uses it as a result rather than executing the query again. So you might ask me, like, what if you send a new query? That's a valid point. So there are conditions to which the query should meet in order for Redshift to return the cached results. And if it does, and if it satisfies it, then only it sends the result query. Like if the cached query matches the query that has been sent, or if the table hasn't been modified. So there are a couple of more conditions based on which it returns the cached query results for you. So it depends on the conditions, and if it does satisfy, then only it will return the result, otherwise it will return the cache. And if it does satisfy, then only it will execute the query, or it will return the cache depending on what type of criteria it has met. The sixth one is compiled code. So the leader node distributes fully optimized compiled codes across all of the nodes of the cluster. So as I already told you about how compiled code is being pushed to the compute nodes, then it is processed using the slices. This is also a very important factor that contributes to the performance. So remember these 5 points for the performance. So first one is massive parallel processing. Second is columnar data storage. Third one is data compression. Fourth one is query optimizer. Fifth one is result caching. And the sixth one is compiled code. So as we already discussed, columnar storage for database tables is an important factor in optimizing analytic query performance, because it drastically reduces the overall disk I/O requirements and reduces the amount of data that you need to load from the disk. This is one of the very important factors for performance when it comes to Redshift. So let's take this example data here of how we see the table structure in relational databases. So we have rows and columns here. So this table that you see here is stored in the disk blocks like this as a part of row-wise storage. So this you have already seen like a million times. And this is what you have already seen and you have already worked on. And this is very effective row-wise storage, and it is optimal for OLTP databases. But when it comes to columnar data storage, each block that you see stores values of a single column for multiple rows. So if you can see here, the virtual IDs 1234 and 2234 and 3211, they are being stored in a single column for multiple rows. And the major advantage that you can see here in this example is that each data block, let's suppose this data block, holds column values for as many as 3 times as many records as row-based storage. And thus, in turn, reduces I/O performance or I/O operations by 1/3 in comparison to row-based storage. And on top of that, this data can be compressed to further reduce the storage overhead. And one more important thing that you should be aware of is that the block size of databases usually ranges from 2 kilobytes to 32 kilobytes, but Redshift uses a block size of 1 MB. So that's huge. So I hope you got the point about how columnar data storage works. And this is just a simple explanation. So if you want to read more about this, please go ahead and read it in the documentation as well. So now let's talk about the integration part of Redshift with other AWS services, like that is using how we can use Redshift with other AWS services. So this is rightly mentioned here that Amazon Redshift integrates with other AWS services to enable you to move, transform, and load your data quickly and reliably using data security features. And these are some of the use cases that you might as well be working on, like moving data between Amazon Redshift to Amazon S3 or between them, or by using Amazon Redshift with Amazon Dynamo DB, or if you want to be like working on importing data from remote hosts over SSH, that's something we as developers tend to do. And also the use case could be automating data loads using AWS data pipelines, and also migrating data using AWS database migration service, that is AWS DMS. So let's talk about them one by one and let's see how these things are done in simple terms. So let's talk about the first one, moving data between Redshift and S3. So when we talk about this, there are 3 steps to this approach of moving data to S3 from Redshift. So the first one is splitting your data into multiple files. Second is uploading files to Amazon S3. Third is using the copy command to load from Amazon S3. So let's understand this better. So when you want to load your data, you can load them as a single file, or you can as well split the data for each table into multiple files. Like you can divide them into chunks and put them to separate files so that you can take advantage of the massive multiprocessing provided by Redshift. And this is something that is recommended. And the files that you divide are recommended to have similar size between like 1 MB to 1 GB, and that too post compression. So let's suppose we have a file called report.txt. We can divide them into multiple chunks, 1, 2, 3, 4, and each of size 250 MB. And you might ask, how is that we can send all of these files together? So what we can do is we can put them in a folder and use copy commands to push all the files by having a collated command. So I know that you might be asking like, what is a copy command? And that's what I'm going to tell you. Wait, so don't worry about that. So what we are trying to say here is you can divide your files into multiple chunks, each of having the same similar size between 1 MB to 1 GB, that is post compression, and you can put them into a single folder and you can push them by using the collated copy command. So how can we make use of the copy command to work with our AWS Redshift? So here we can make use of copy command to load a table in parallel from data files on S3. So you have to keep in mind that we are talking about loading data from S3 to Redshift. And this is the command. So copy table name from S3 / bucket name / object prefix and the authorization. So where you make use of IAM to provide the principal. And to supply multiple entries to the command for our chunk of split files, we make use of something called a manifest file. So a manifest file is like your JSON, and you can add the entries of your chunk files like this. And this can be used in your copy command to load the data from S3. And this file, you can place it in your S3 bucket folder along with other files that you have. So let's suppose we have added all the entries in the report.manifest. So this is our report.manifest. So this is part 1, this is part 2, this is part 3, this is part 4. And if you see, we have entries and within which we have the list of files. Okay, as a part of the S3 URL. And then you see there is a field called mandatory, which is a Boolean, rather it could be true or false. So this is an optional mandatory flag that specifies whether copy should return an error if the file is not found. And this flag is kind of a okayish feature, I feel, as this indicates whether copy should terminate if the file does not exist. And if you see, the default value is already false. So that is why I said it's okay, because regardless of any mandatory settings, copy terminates if no files are found. So now let's see the command with the manifest file. So if you see here, so copy table name from S3 bucket / manifest file, authorization and the manifest. So the final query that you will have is copy customer. So this is the table name from S3 reporting is the bucket, which will have the report.manifest file. And this is my IAM role that I'm providing, which has the permission. And this is the manifest command that I have. So here we specify the authentication for it to work. So now you know how we can pull the data from S3. So what is that the next thing that we have to do? So now let's talk on how we can unload data to S3. So once you have executed the query, you get the result, and that result can be unloaded to S3. So just like we have copy command to get the data from S3, we also have an unload command which actually does the opposite and helps you unload the query results to S3. So now let's see how the unload command works. So unload select star from reporting. So here the command is unload and we are executing a query or the select query that Redshift supports. And apart from this, you can have a limit clause on the outer select. So you need to be wary about this condition as well. And then we have two S3 reporting reports unload report underscore. So then that is the two path. So the path to the S3 to which we want to send the data. Then as usual, you provide the IAM rule ARN that you have. And that is basically acting as the authentication for you. So just like we had the option to divide the files for processing here as well, unload writes data in parallel to multiple files according to the number of slices in the cluster. So if you want to unload at once, then you can specify the parameter parallel as off. As you can see in the command here, the maximum size for a data file is set to 6.2 GB. And let's suppose you wish to limit the size, then you can specify a parameter like max file size that I have specified as 100 MB. So where max file size denotes the parameter of the size that you wish to limit your file to. And another feature that I really liked about Unload is that it can automatically create files using Amazon S3 server-side encryption with AWS managed encryption keys, that is SSE S3. So as you can see here, we can provide the KMS key ID parameter, which has the key ID or the key, and we can upload the files or unload the files by encrypting them. So that's a very good thing. So you can follow this as well if you want your data to be more secure. There's one of the things that I really liked. So next up for us is using Amazon Redshift with Amazon Dynamo DB. So there might be a situation where you might have to work with Dynamo DB. So you can use the copy command to load a table with data from a single Amazon Dynamo DB table. So let's look at the syntax to grab values from the Dynamo DB table. So the syntax is copy Redshift table name. So this is the Redshift table name that you have. Then from Dynamo DB / Dynamo DB table name, this is the Dynamo DB table URL. And then we have the authorization. Here you will specify the IAM permissions and the read ratio of integer. At the end, we will specify the read ratio. Now on the right hand side, we have the actual command where we specify the Redshift table name as reporting, and we specify the Dynamo DB URL for table from which we want to fetch the data. And then we provide the IAM role for our authentication, and the read ratio is set to 50. And you can execute this to fetch the data from the single table. And I know you might be thinking, what is read ratio? And why did I set this to 50 like an integer value? So when we create a Dynamo DB table or we create the Dynamo DB database, we must specify something called as the provision throughput capacity. Okay, so it's provision throughput capacity. So which is the amount of read and write activity that the table can support. So when your application is reading or writing more than what the table can support, then Dynamo DB returns provision throughput exceeded exception. So while working with production data, you don't want to have a huge throttling, and in order to reduce it, you must set the read ratio value much lower than the average percentage of unused provision throughput. Okay, so that is why I set it to 50. Or if I set the max value of 100 for read ratio, it will make use of the entire provision throughput. So here we can set the value to 50 so that it consumes up to 50% of the provision throughput value. And this value is what you give. And if you are aware of the average percentage of unused provision throughput that you have set, then you are good to go. And there is a very important thing that we should note here that has been mentioned by AWS is that the Dynamo DB table that provides the data must be created in the same AWS region as your cluster, that is your Redshift cluster, unless you use the region option to specify the AWS region in which the Amazon Dynamo DB table is located. If you specify this, then it is fine, or else it must be in the same region as your cluster. So this is something that you need to be aware of when designing your queries with Redshift and Dynamo DB. So I hope that was clear. Let's move on. So now let's talk about the way we can connect to Redshift with SSH for our remote hosts. So imagine these are your instances and this is the Redshift cluster that we want to connect. Quite neat, isn't it? We have 4 instances and we have the Redshift cluster. So whenever you wish to connect to services like databases, there are constraints like it could be behind a private subnet or bastion host. But the mechanism for SSH, the base of how we connect to hosts using SSH, always remains the same. I'll tell you why. The first 4 steps that you see here are related to direct key connection with host and cluster. Here in these first steps, you first retrieve the cluster public key and cluster node IP addresses. For this, you make use of AWS Redshift describe cluster command. So -- cluster identifier. So this command, if you use, you will get the list of the cluster node IPs and you can make use of that. So there will be multiple private and public IPs based on the cluster nodes that you have, and these IPs can be used to add as a part of your firewall or security group. And just like you connect to SSH with the key, you can do the same here as well. So add the Amazon Redshift cluster public key to the host authorized keys file that we got from the previous step. So this is basically your first 4 steps. The next step that you see here are important. So just like we discussed before, while using the copy command, we created a manifest file. Here as well, we can create the manifest file for connection. And you can create your manifest file like this. So you can create the file with the entries of the endpoints, that is your node IPs, and the command that you want to execute, and then you can add the public key to your manifest file. So that will be the path, or you can specify the public key itself. And if there are multiple nodes, then you can create a list of these parameters, and then by using this manifest file, you can run the copy commands. So now let's see how we can automate the process of loading data to Redshift using S3 and AWS data pipelines. So here you can see S3 bucket with the CSV file with the input data that you want to store in your Redshift. So this CSV will be stored in your S3 cloud, and using data pipeline. Okay, if you don't know what data pipeline does, I'll tell you in simple terms for you to understand this design. So data pipeline is the managed ETL service. With this, what happens is you can move or transform data which you provided. So you can move or transform the data. And there is a definition that you have to provide for the data pipeline, and that is basically your business logic that you define for your data to be processed. And then you can create tasks that can help you move your processed data to the Redshift cluster. So that's the whole idea. As a data pipeline helps you automate the steps to move and transform data. It makes it easy for the users to use it with Redshift. So you have your S3 bucket, which has the input data. You can use your data pipeline to move or process the data that you have by creating business logics. And then you can move the data or transform the data and move it to the Redshift cluster. So this is how you can use S3 data pipeline to work with Redshift. So now let's talk about migrating data using AWS Database Migration Service or AWS DMS. So we know that AWS Migration Service is used to migrate databases to AWS. So we will see how we can use it in conjunction with Redshift. So here, if you see, we have our databases ready that we want to migrate to Redshift. So this could be your MySQL or PostgreSQL, or it could be another database on your AWS cloud or on-premise. So it can be any of the databases that you have. So AWS Data Migration Service or Database Migration Service supports homogeneous migrations such as Oracle to Oracle, as well as heterogeneous migrations between different database platforms such as Oracle or Microsoft SQL Server to Amazon Aurora. So this supports the both ways, like homogeneous and heterogeneous migrations. And here DMS first moves data to an Amazon S3 bucket, and then it moves to the Redshift cluster. And then once it is on the Redshift, you can query and use it for your analytics or reporting or data mining. And the good thing is that when migrating databases to Amazon Redshift, you can use DMS free for 6 months. And then you can request an extension of 3 months. So that becomes for a total of 9 months by opening a support ticket. So that's a very good thing. So if you want to do it, you can do it now as well. So, but there is a constraint here that if you enable multi-AZ, you have to pay the full cost of the DMS instance. So you have to understand that it is not all free, but if you don't enable multi-AZ, it will be free for you for 6 months. So you can use that, I feel, yeah. So now this section is also very important, and here we are going to discuss about enabling private access to Amazon Redshift from your client applications in another VPC. So as you can see here, we are talking about using Redshift managed VPC endpoints. Our main goal here is to privately access our Redshift warehouse, so which is basically in another VPC from our applications in our own VPC without using public IP. So that's the basic idea, isn't it? So let's understand what it was like before Redshift managed endpoints and how did the connection work. So when we did not have Redshift managed endpoints, if you see on the right hand side, if I am someone who is hosting the Redshift on the VPC, I would create a network load balancer. I would create a network load balancer or NLB, and I could as well automate the NLB target groups to the active IPs of the Redshift endpoint in order for my user to make use of it. So these things I can do as a part of my provisioning, because I have the Redshift cluster. I can create the NLB. So my users in another account can have their BI or ETL tools or database viewers or SQL Workbench on the EC2 instance. And by using the internet gateway, they can connect to this by connecting to the network load balancer endpoint and via internet access. So this design is basically before how we did it when we did not have Redshift managed endpoints. So let's check out with managed endpoint how it actually changes. So now by using AWS Redshift managed endpoints, that is using private link, we can create our endpoints in our VPC and securely connect to the Redshift cluster. So that is a very good thing for us now. And you have to remember that Amazon Redshift supports cross VPC access using Amazon Redshift managed VPC endpoints. So it's a very good thing. Now, if you have to use the Redshift that is another VPC, you can create your managed endpoints for Amazon Redshift or AWS Redshift. So here you can see on the right hand side, we don't need to manage the cluster or the load balancer, as this is handled by the Redshift or Amazon Redshift itself. So you might ask how you can make use of this. So once this is set up, you will get the connection string to connect to the cluster. So this makes it easier and more efficient because you have less things to manage. So everything will be managed by your Amazon Redshift managed VPC endpoint. You can just connect the endpoint to this particular endpoint service, and then you can make use of it. So this is a very good thing. So everything remains secure and you are able to connect to the Amazon Redshift securely. So there is one more important feature of Redshift that we can discuss in short so that you know that it exists. And if you come across performance related to Redshift, you can as well think about this. And that is Aqua, Advanced Query Accelerator for Amazon Redshift. The first thing that you should be familiar with is the acronym of Aqua, that is Advanced Query Accelerator. And if it is a query accelerator, then obviously it is for speeding up the performance when it comes to large data sets, which might take more time in normal situations. So that is basically the whole idea that you should think about, because it is an advanced query accelerator, so it must be related to the performance. So what is the problem here and how Aqua is going to resolve it? So that's the major question that we have, and that is what we are going to find out. So what are the challenges with existing data warehouse architectures? You need to understand that when it comes to data and its movement, the major factor is the storage and how we process and move data and query results. So the first one is network bandwidth as a bottleneck. So when you're working with Redshift, you know that when we send a query, it is being processed by the leader node and we make use of the centralized storage, and then it moves to the cluster nodes for further processing and it returns the result. And over time, when the amount of data increases, the network becomes a huge bottleneck when you consider movement of the data. So that is one of the first points that we need to understand. And the other thing is CPU in memory processing. So as I already told you before, when we have the columnar data storage or columnar storage, you tend to load very less data into memory, which helps Redshift to have a better in-memory processing performance when executing the queries. But with growing data, if you see, the processing over time scales only twice or 2 times over a span of time. So even though if you improve the network bandwidth, the CPU will still remain the bottleneck. So how do we solve this? Yes, the solution is Aqua, and here we are trying to improve 3 or more areas. So first we want to remove the network bandwidth limitation using a better processing power and using a scale out architecture. Now I want you to focus on the left hand side where we have the Aqua architecture. So here what it does is Aqua actually uses custom AWS designed processors to improve data processing by using a scale out architecture to accelerate data processing. So here what happens is, so Aqua uses Redshift RA3, RA3.4XL and RA3.16XL processors, and you can use these in specific regions. So remember that. So these are the processors that are compatible with Aqua, but they are available in specific regions. So it is a bit weird that AP South is not supported for this, but you can check the locations which are being supported for RA3. So with RA3.16x large instance, we have 48 vCPUs, 384 GB of memory, and up to 64 terabyte of storage. And these instances are created in the vision of managed storage processing. So that is how it is basically scaling out the architecture for you so that it actually helps you to process the data faster. So if you see here, Redshift uses custom designed hardware, and for the storage, it uses high-speed non-volatile memory express NVMe. This is very popular right now. So this is basically a solid-state storage drive and Nitro-based acceleration for compression and encryption. So NVMe actually creates a lot of performance benefits when it comes to storage. So this is something that has been upgraded to. And on the right hand side, you can see the cluster design form. And here Aqua can only be activated in certain AWS regions and for RA3.4x large and RA3.16x large node types only. So when you choose these two, you will get the option of advanced query acceleration, and you can just choose either automatic or turn off or turn on. Other than that, RA3 can also create your cluster with DC2 instance types, which make use of a fixed solid state drive as a part of the storage. I know you must be thinking of a demo. It's coming up shortly on the channel. And if you're watching this on the website, it'll be added in sometime. So don't worry about this. But we have to understand, so there are two things here, RA3 and DC2. So these two are the ones that actually make a major difference here. So in DC2, if you see, we have the SSDs, and on RA3, we are going to make use of the NVMe. And this actually creates a lot of difference when it comes to performance for the storage, or the compute storage, or the memory efficiency. That is why Aqua is going to perform better, because it is designed to perform better. And if it does not, then it is a failure in the part of AWS. But the compute nodes that you see here are always working on high-speed networks. So you don't have to worry about the network bandwidth. So as I already told you, even if you increase the network bandwidth, the CPU was becoming a bottleneck, and this will not be the case now. So here we are at the end of the AWS Redshift, and Redshift is a huge complex architecture of a database with a lot of concepts open for discussion. That is why it is not possible to cover them all in the time span that we have, but we will keep on creating videos on Redshift covering different aspects of this. But what we have discussed today about Redshift is also very valuable, and it will be really helpful for you. So I hope you liked it. So let's move on. Now we move on to a very special database, which is AWS KeySpaces, a scalable, highly available and managed Apache Cassandra compatible database service. So many terms to discuss, isn't it? So let's get started. So Amazon KeySpaces for Apache Cassandra is a scalable, highly available and managed Apache Cassandra compatible database service. There are a lot of terms, isn't it? So I'm not sure how many of you have used Cassandra before, but don't worry, I'll give you a small introduction to Cassandra so that you can relate to while using Amazon KeySpaces. So don't worry about that. So just like we have RDS for Postgres, we have KeySpaces for Cassandra, and you will get to know why this is called Amazon KeySpaces. So it's more about Cassandra than about Amazon on a lighter note. So what are the advantages of using KeySpaces? So first of all, you don't have to provision, patch or manage servers. Secondly, you don't have to install, maintain or operate the software, that is Apache Cassandra. So in simple terms, it is easier to manage Cassandra and having less overhead on managing the clusters and nodes that you might have to do when you host Cassandra yourself for your applications. And the other important advantage that we have here is Amazon KeySpaces is serverless. So you pay for the resources that you use, and the service automatically scales tables up and down in response to the application traffic. That's easy, isn't it? Moving on to the additional benefits of using KeySpaces. So first one is compatible with Apache Cassandra. So as a developer, we make use of Cassandra query language, and we use the drivers to work with Cassandra, isn't it? So here as well, it becomes very easy because you need to just change your connection parameters to work or to connect and work on the data that we have. And the next one is no servers to manage. As I already told you that you don't have to provision, patch or manage servers. And secondly, you don't have to maintain or install or operate the softwares that you have. So in simple terms, it is easier to manage Cassandra and having less overhead on managing the cluster. Third one is performance at scale. This means that based on your demand, the capacity scaling becomes very easy because it is automated and managed by AWS. So we can create applications with virtually unlimited throughput and storage that can serve thousands of requests per second without the need of capacity planning. But you pay for what you use. So highly available and secure. For high availability, Amazon KeySpaces offers a 99.99% availability SLA within an AWS region. And for security in Amazon or AWS KeySpaces, the tables are encrypted by default and replicated 3 times in multiple availability zones. So remember these points very carefully. So if you're using Amazon KeySpaces, it's very easy for you to work with Cassandra because Amazon KeySpaces makes it easy to migrate, run and scale Cassandra workloads in the AWS cloud. And if you have worked on Cassandra, you know that we create key spaces here instead of databases. And here as well, you can create key spaces and tables in Amazon KeySpaces without having to worry about deploying the infrastructure or installing any software. So having said this, I would any day use Amazon KeySpaces given that I don't have to set up the Cassandra cluster and manage the nodes, its consistency and installing drivers for Python. Yes, I would. I might be joking on this one, but yes, if there is an easier way to work with Cassandra, why not? So let's look at the high-level architecture for Apache Cassandra here. So Cassandra in simple terms is an open source NoSQL distributed database. So if you wish to work with Cassandra, you can install it on your machine or even by using Docker. So if you see the third point here, that Cassandra actually works on horizontal scalability, and I'm sure you guys must be aware of what horizontal scalability is. So it's like, if you don't know, like it's like if you're hungry, you don't take a 12-inch sub, you take two 6-inch sub from the Subway. So here also you keep on adding more nodes in order to scale it to meet your demand. So if you see here, we have 4 nodes and one installation is equal to 1 node, or it is considered as one installation is considered as 1 node. And each node that we have is connected to each other. So it will be working as a peer-to-peer architecture. So here you don't have a single point of failure. Each node that we have here is capable enough to perform database operations, and more so without the need for a master node. That is why it is known to be a distributed architecture. And Cassandra node communication works on a gossip protocol. So I hope that you must be aware of what gossip is. Yes, we do a lot of gossip. So if I am a node, I need the information about other nodes. So in a gossip protocol, every node gossips or talks with up to 3 other nodes every second to find out the status of other nodes. So if you need more power or performance in Apache Cassandra, you can add more nodes to that to increase the performance. And when you create tables in Cassandra, and for every table that you see, the first value, the first field is the partition key. And why is it called a partition key is because the hashed value for this is used to determine which node the data should be stored in. So we have the table here, the first field that you see of the column actor. We have John, Sam, Goldie. These are the values, and its hashed value is used by the partitioner to create the token and in turn determine where the data has to be stored. So if you see here, we have node 2, which has the ID 62 or the token value 62. Node 3 has 50 and 50. And similarly, we have node 1, which has the ID for the partition key as 45. So this is the way that it has been partitioned and it has been stored. So now let's talk about how we can work with Cassandra using CQL. So if we wish to create a key space, you can call it like creating databases. So create key space and you provide the name of the key space. Here I have given movie buff with replication is equal to class : simple strategy, and the replication factor is 3. So I know you must be thinking what is replication and what is a simple strategy and replication factor. So don't worry, we will talk about that. So now let's create our table that is movies. So create table name that is movies, and I have provided 5 fields here. Actor that is text, movies text, budget text, year also text, director is also text. Basically that is the name. So here you can provide the data types and the columns that you want, and then the important part is the primary key. So here if you see, I have a primary key that I have created that is actor, movies and budget. So this is the combination of keys that I have used to create the primary key. And if you see here in Cassandra, we can create compound primary keys, create columns so that you can query and return sorted results. So sometimes what happens is there can be repeated values in a column. So you can have multiple columns and pair them together to make your primary key. And there are a few concepts that you need to understand. One is primary key that you know already by now. The primary key is a key to indicate one or more columns which we can make use of to retrieve data from the table. Next thing is composite primary key or compound key. For example, I want to take 2 keys and make them the composite key, like I have here actor and movies. So these 2 together can make up for my composite key. And the first part of the key is called the partition key, which is responsible for data distribution across your nodes. And your composite key will be used for sorting. A partition key is the same as a primary key when the primary key consists of a single column. And the second part that you see in this case actor is the partition key, and movie and budget are the clustering keys. And for a simple primary key, like if suppose I want to have one value itself, so we can make use of a unique value. So in this case, we can make use of something like a UUID as a primary key. So that will be unique. Now that you have some idea about Cassandra, this is not going to be more about Cassandra, but about KeySpaces. So let's discuss on that. If you see the design here as a developer, it actually works on our part because with Cassandra, we have ways to connect to the database. So we can make use of the Cassandra driver, or we can also make use of the SQL SH from our instances. And also we can work using Amazon KeySpaces console. And with Amazon KeySpaces, you get two throughput capacity modes for reads and write. That is one on demand and provisioned. So either you can choose how many throughputs you need and you can scale it as per requirement on demand. But more users often prefer using on demand if they are not sure on how their traffic fluctuates, because in on demand you pay only for the reads and writes that your application actually performs. So that's a better way to do it. But the only thing that you have to keep in mind is you can change the capacity mode of your table once per day. And Amazon KeySpaces stores 3 copies of your data in multiple availability zones for durability and high availability. And as you can see here, we have encrypted storage, as encryption at rest is automatically enabled when we create a new Amazon KeySpaces table, and all the client connections require TLS security. So that's a very good thing. So let's talk about a few points that we need to keep in mind when working with Amazon KeySpaces. So Amazon KeySpaces actually supports Cassandra Query Language or SQL API version 3.x. And if you're working with 2.x, then don't worry, it is backward compatible with version 2.x. So that's a good thing. And you can run your Apache Cassandra workloads on AWS using the same Cassandra application code. So you don't have to change much when you're moving to KeySpaces. And Amazon KeySpaces also supports all commonly used Cassandra data plane operations, such as creating KeySpaces, tables, reading data and writing data. So this is also very helpful for us. And the best part here is that Amazon KeySpaces is serverless, so you don't have to provision, patch or manage servers. So there are very less things to worry about for the users when it comes to managing the cluster. And for me, the biggest advantage I would say is that the settings such as replication factors and consistency levels are configured automatically to provide you with high availability, durability, and single digit millisecond performance. So this is something that I am really looking forward to. And most of the times as an admin, it's a tricky job to have replication factors and consistency levels in place. So if it is done automatically, then it's just an awesome thing to have. So the next important thing for us is to understand that how replication factor and consistency level works. So imagine a scenario where you have 6 jars of cookies. So imagine a scenario where you have 6 jars of cookies that we love to eat, and you have 5 rooms. And you cannot predict which room is going to get locked at any given point of time. So storing all the cookies or cookie jars in a single room will be a very bad approach, isn't it? So what we do is we take one cookie jar each and store them in 3 rooms individually. And in this case, if room 1 gets locked, then also we have 2 more rooms from which we can get the cookies out and eat. And this is just an analogy in similar ways for your data that is written or updated to KeySpaces. And Amazon KeySpaces stores data replicas on multiple nodes to ensure reliability and fault tolerance. So that's a very good thing. The total number of replicas for the key space across a cluster is referred to as the KeySpaces replication factor. Okay, so remember this point very carefully. The total number of replicas for a key space across a cluster is referred to as the KeySpaces replication factor. So if the replication factor is 1, then there is only 1 copy of the row of your table on the cluster. Okay, that's a sad thing, but yes, that is one way to put it. So if the replication factor is 2, then 2 copies of each row is on the cluster, where each copy is on a separate node. Similarly, replication factor of 3 means that there are 3 copies of each row and each copy is on each of the different nodes. So I want you guys to focus on the image here and think of these 4 nodes that we have. Okay, node 1, node 2, node 3 and node 4. Consider each of them as the replica node. And remember, the replication factor that you set should never be more than the nodes that you have in the cluster. So for example, if you have 4 nodes, the replication should not be more than 4. In ideal scenarios, we should have 3 or 4 nodes for our cluster. And based on replication factor, we determine the consistency, and when it comes to Cassandra, you will hear this word quorum consistency a lot, which will ensure how many nodes will respond when we set the read and write consistency. And there are types of quorums as well. And the way we calculate quorum is the sum of the replication factors, as I mentioned here, the sum of the replication factors by 2 plus 1. So let's take an example here. We have 2 DCs with replication factors of 3. So if you can see, DC1 is RF3 and DC2 is RF3. So quorum will be 3 plus 3 by 2 plus 1. So that is 6 by 2 plus 1, that is 4 nodes. 2 nodes down in the cluster for its read and write consistency. So consistency here will manage the availability and the accuracy of the data upon which your read and writes are based on. And the other thing that you see here in the create space is that replication strategy, or the strategy that we have is class, that is simple strategy. So simple strategy works if you're working with multiple nodes in your data center. And similarly, we have local and network topology strategies. You can read more about them. So, but this is more about working on which strategy you're going to use based on what is the type of architecture that you have. Now let's see some of the consistencies with both read and write. So the first one that we have is the table that describes the write consistency levels from strongest to weakest in that order. So the first level that we have is all. So this provides the highest consistency and the lowest availability of any other level, because the data is written to all the nodes, then only it is said to be successful. Even if one of the nodes fail, then the write operation actually fails. Okay, so these values that I'm saying, all the levels that I'm saying right now are for write, but they transpose equally to the read consistency. So if you understand how and exactly the write works, then the read is oppositely similar. So don't worry about that. And the next one is each quorum. So this also provides strong consistency, but let's suppose you have 3 data centers and you have 3 replications. Then it says it should reach quorum on each of the data centers. So it means that out of 3, at least 2 should be successful for the write. So let's suppose you have 3 data centers and there are 3 replica nodes for each of them. So when we say that it should reach quorum, it means that, so what it means is that if it has a replication factor of 3 for each data center, then you have to calculate like 3 by 2 plus 1. So it will be 2. So at least 2 should be having the proper data. Then only it will consider it as successful. And each quorum means each of the data centers should have the quorum value or the quorum attained. Next one is quorum. So here, based on the example, 3 plus 3 plus 3, that is 9, by 2 plus 1, so that is 5. So any 5 nodes is successful, then it is a success. The next one is local quorum. It means that if you have 3, out of them 1 local DC should have quorum, that is 2 nodes. The next one that we have is 1. So here we need 1 node from any data center to succeed. And the other one that we have similar like 2 and 3. So they need 2 or 3 to succeed. Similarly that we have. The next one is local 1. So when you send the write, if you get acknowledgement from any node, then it is a success. And that too from the local data center. Next is any. So this tells us that if it is written on any of the nodes, it is a success. So I hope you got the point here. So each quorum, local quorum, 1, 2, 3, local 1 and any. So these are basically like the consistency levels from the strongest to weakest. And if you want, you can just pause here and read more about this so that you can get more information about it, because we have this similar to what we have on the read. But the problem here is, if suppose you are willing to have the highest consistency, there will be a problem with the availability as well. So keep in mind that even if you provide the highest consistency, the lowest availability is the one that you're going to face. So you have to keep in mind both the ways, like you can't always achieve for highest consistency because you might compromise on availability. And when it comes to Amazon KeySpaces for write consistency, Amazon KeySpaces replicates all write operations 3 times across multiple availability zones for high availability. And here it uses the local quorum consistency level. So write consistency for Amazon KeySpaces uses local quorum. So local quorum means consistency of 2 from the local data center. That is, if you have 3 data centers, out of them, one local DC should have quorum, that is 2 nodes, if you have a replication factor of 3. And for the read consistency levels, Amazon KeySpaces supports 3 consistency levels, like 3 read consistency levels, that is 1, local 1, and local quorum. So I know that you already know about these, but you have to understand that other consistency levels are not supported. So you have to make use of these 3. And as we have already discussed on this one, you can read more about this. And what we have discussed till now is more than enough for the solution architect, but it's up to you. And I would request you to go through the documentation as well. So now we have covered the top 4 databases on the list. Let's talk about Amazon Neptune. So Amazon Neptune is your fast, reliable graph database built for the cloud. So we have a lot of graph database already, but Neptune is a graph database which is offering from AWS for users who want to use graph database as a part of the cloud design that they have. So fast, reliable graph database built for the cloud. So if you understand what is a graph database, then it's sufficient for you if you're just looking to cover the concepts for your certification exam. But as you know, we discuss things a bit more in depth here. So let's do that. So this is a normal table that we have seen a million times. So let's understand the table data of a social media website here. So we have Jane. She is a female of age 22 who likes music and follows Kane. And Kane is a male of age 32 who likes music and movies and follows Jane. And Susan. Similarly, we have Susan. She is around 30 years of age and she is a female and she likes movies and follows John. And John is 31 years of age, likes music, follows Jack, and Jack likes movies, is of 22 years of age, is a male, and follows Susan. So this is basically a graph representing the social networking that we have. So as we are discussing about graph databases, let's depict this, or let's represent this in a graph database. So let's see how we can depict this. So let's consider our first node to be Jane. So node in graph databases are entities that have properties attached to them like gender, age, name. So you can have them. So these are called nodes. So we have the first node that is Jane, and she has a relationship that is follows to Kane because she follows Kane as per the database that we have, and has another relationship that is likes for movies. Now let's move on to the next row. We have Kane. So we have Kane, which is a node with age and gender as the properties, and the relationship that we have is Kane follows Susan and Jane. So you can see here we have the arrow directing towards the relationship follows towards Susan and Jane. And Kane also likes music and movies. So these are the 2 relationships it has, which is of nature likes. And similarly, we have the network for other rows as well. And this is how we imagine the graph database. So here, if you see, Susan actually follows John, and John likes music, and Jack also follows Susan and likes movies. So in this way, we are trying to imagine this as a graph. And this is how you imagine the graph database. A graph database, or GDB, is a database that uses graph structures for semantic queries with nodes, edges, and properties to represent and store data. So that is how we are going to imagine this. So we have the edges, which shows the relationships, and nodes, which are the connection points, as you have seen here. And you can see the directions in the relationships, and you know why it is important here, because it denotes who actually has a relationship of what nature with the other person or the other node. So now let's talk more in detail about this. So in the graph database, nodes that we have can hold values like key value pairs, like name equals Kane and age and gender. So these are the type of properties it can have, and they can hold any number of attributes like key value pairs called properties. And nodes can be labeled, and if you see the edges, we have represented them as relationships as follows, and it has a direction that states what is being followed to or who is being followed to, and they connect nodes with each other. So let's suppose we have 3 tables here: people, people follow, and followers. So in people, we have the name of the people, and we have the ID of the follows. So when it goes to people follow, we have the ID of 01 here. And here it is the name of the followers that is denoted by the ID. So 1 and 2. So if you see 1 and 2 is denoted by the ID of Jane and Susan as the name. So if I have to draw a relation, then for the follows table, my ID of Kane is 01. So whatever ID that is 01 here and adjacent to that, if there is an ID, it means that Kane follows that particular ID. So let's suppose it is 1, then Kane follows Jane, Kane also follows Susan. So that's how it is being represented here. So Kane follows the ID 01, and on people follows table, ID 01 has the value 1, which has a relationship with the third table followers, and with ID 1, the name that we get is Jane. So first let's talk about the SQL query. If I want to find who follows Jane, so let's suppose I want to find who follows Jane. So I can use a join clause like select name from people, left join of people follows on people.follows equal to people_follows.id. Left join followers on follows.id equal to person_follows.follows.id. So this will be the ID that I have. So where followers.name equal to Jane. So I'll get the data here, or basically Jane. I am not sure I have written this in random. So if this is wrong, then please don't curse me on this one. You can just suggest me if this is wrong. You can try it on your own. So this is a simple query for SQL when it comes to getting the data. So let's see what difference can we have with the graph database. So here I'm using a cipher statement. So match p.people, and if you see in the middle that I've highlighted as yellow, so you can see there is a relationship that it is trying to point out to us, like colon follows, and you can see that it is denoting it with a arrow mark where d.name is equal to Jane and return p.name. So p.name is basically Kane. So it's a very simple way to get this using the cipher query. So now that we have some idea regarding the graph database, let's move on to the Amazon Neptune database. And I'm just giving you some very basic ideas about how this graph database is different, but there are a lot of things that we can discuss, but I don't think so it is very much important in the context of what we are trying to discuss. So now let's talk about Amazon Neptune. So Amazon Neptune is a fast, reliable, fully managed graph database service that makes it easy to build and run applications that work with highly connected datasets. So highly connected datasets is the most important pointer that you have to understand. So it provides us with high availability with read replicas for the data that we have, that is your table data that is replicated automatically, as Neptune replicates 6 copies of your data across 3 availability zones. And it is fully managed by AWS. It also gives us point-in-time recovery. You can take continuous backup of your KeySpace table data, so that in case any accident or failure occurs, you can restore the tables to any second in the preceding 35 days. And having said that, you also get to have continuous backup to Amazon S3 for the data that can be archived as well. And for security of your data, you have HTTPS encrypted client connections and encryption at rest for the data. And Amazon Neptune is fully managed, as you know, so there is no need to provision or no need for hardware provisioning, software patching, setup, configuration, or backups. So that's an added advantage that I would say. So let's look at some of the examples and use cases of Amazon Neptune. The first one is knowledge graphs. So with Amazon Neptune, you can use graph queries that enable users to easily navigate highly connected datasets. And in turn, we can create an environment where the data querying becomes very efficient. So if you see, a knowledge graph actually is built specifically that can help users to find details about their interest. So if you see here, we have users Bill, Alice, and Bob. And Bob has a relationship that is interested in Mona Lisa. So if he has to find out where he can visit to watch the painting Mona Lisa, or where he has to visit, which place he has to visit to see Mona Lisa, he can actually use the relationship that Mona Lisa has with the Louvre Museum. That is, it can be found out with the relationship that is exhibited at. So Bob can use this information to visit that museum and see the Mona Lisa's painting or the picture that we have. So this is just a simple example that I'm giving you, but there are a lot of information that you can draw it from. So this is how you can also create your own graph database, and you can also visualize things like this. The second one is fraud detection. Sometimes what happens is that a fraud person can make use of a credit card information and try and purchase products. So he or she might be aware of your credit card number and email, but using graph databases, we can create relationships or relation with the credit card holders, the location and the previous purchases to detect if there is any anomaly. So if there is illegal purchase being made, then we can stop it and detect fraud transactions. So this is a very important use case for graph databases. The third one that we have here is social networking. This is very popular, isn't it? As we spoke before. So you have users, and if you want to find relations of who follows whom, I know most of you do that, stalkers do that, but this is how social media works. It's all about relationships. So you can find out, or you can draw relationships by using interconnected data using the graph database. And the fourth one that we have here is network and IT operations. When it comes to network operations, the most important thing is events. Which hosts are a part of what application, what is the status, and how they are connected. These informations are really important. So there could be thousands of devices, and with the help of the graph databases, we can capture the network events and query them effectively so that you can find out which data points that you need for a particular instance or a particular host. And you can find out the relationship of what and where it belongs to. Now let's talk more about the Amazon Neptune engine. So Amazon Neptune engine is optimized for storing billions of relationships and querying the graph with milliseconds latency. So it is very, very fast. So you're dealing with a service that can capture or query data and not small amount of data. They are events, relationships, and they query them for you in a millisecond or less than that. And in your exam, if you find a question related to graph database, you know what to choose. Yes, that should be Amazon Neptune. And as you can see here, we have mentioned that Amazon Neptune supports popular query languages or graph query languages such as Apache Tinkerpop, Gremlin, W3C SparkQL. And as we already discussed about the powers of using Neptune graph database and the use cases, so it can be used with recommendation engines, fraud detection, knowledge graphs, drug discovery, network security, and just like that. And just like the other databases, we discussed Neptune is a fully managed database, so hardware provisioning, patching, and other configurations are not your headache. So I would like you to focus on the image on the left-hand side here now. So here on the left-hand side, I just want you to focus on Kane, Susan, and Jane for now. So here data is stored at the vertices, which are also called as nodes, as we discussed before, and the relationships are denoted by the edges, and edges have a type like follows or likes or friends, as we have in this case. And they have a direction, so it tells you where it starts from and where it ends. So if you see, we have a relationship friends, which starts from Susan. No, it starts from Kane to Susan. So that is how it is denoted. And relationships are also called predicates. So remember that. Mostly you would find Neptune database used in places where you might find a lot of interconnected data with a lot of connections and data related to each other, and where we want fast retrievals. And AWS has a very important line, or tells a very important line here, that a graph database like Neptune can query relationships between billions of vertices without bogging down. So without much lag, you will find yourself having the data that you need and when you need it. So now let's talk about the simplified view of the Neptune architecture. So we have our applications that we were actually working on, that we are working on. And Neptune supports popular graph query languages and data models, and we can make use of SparkQL or Gremlin based on our current architecture. So this will help you connect to the database and help you query the data that your application wants. And which is obviously managed by the Amazon Neptune setup that you have. And you can bulk load data from S3 as well. And as well, using the console or API, you can manage the configuration, and the DB snapshots are taken using that as well. Next, to provide you the high availability and fault tolerance, we have the read replicas and the multi-easy setup. So it provides us with high availability with read replicas for the data set that we have. And that is your table data that is replicated automatically, as Neptune replicates 6 copies of your data across 3 availability zones. And it is fully managed by AWS. And the other benefit that I've already told you is point-in-time recovery. So you can continuously back up your Amazon KeySpace table data, so that in case if there is any accident or failure, you can restore the table to any second in the preceding 35 days. And you also get to have continuous backup, as I already said you before, to Amazon S3 for your data that can be archived as well. On the right hand side, we have some differences between RDS and Neptune. Both the places you have the max data volume that can mount up to, that is 64 terabytes. But the difference is that in Neptune, you are charged for the storage that you consume, not the total 64. That's a very good thing, isn't it? And when it comes to interface for RDS or Aurora or serverless, we have and make use of SQL. And here on Neptune, we make use of Gremlin or SparkQL. And when it comes to replication and availability for RDS, Aurora and serverless, we make use of multi-AZ, multi-region, and you can avoid replications as well. But here in Neptune, you have only multi-AZ. And then we have the database structure. So for RDS Aurora, we make use of the relationship model or relational model. And here on Neptune, we make use of the graph. So I hope it was clear. This is a very interesting difference that you can note down, and this will be really helpful. So I hope you got the point. Let's move on. To understand the architecture of Amazon Neptune, we need to talk about a use case here. And in this use case, we will talk about connecting to Amazon Neptune from the clients outside the Neptune VPC using AWS network load balancers. And this can also be achieved using an application load balancer, but let's try and understand this first. But before that, we need to talk about three major components of Neptune. The first one that you see here is primary DB instance. So every Neptune database cluster has one primary DB instance that is used for your read and write operations. And the primary database instance is responsible for all the writes and operations performed to the volume that you have on the cluster. Don't worry about this, just listen to what I'm saying right now. The second one is the Neptune replica. So replica, as you might know or you might be aware of, is responsible for the read operations. And here the Neptune replica connects to the storage that is being used by the primary database instance. So here the Neptune database cluster can have up to 15 Neptune replicas apart from the Neptune DB or primary database instance. So in total, you can have 16 replicas along with the one that you have, that is the primary database instance. And for high availability, we can have our replicas in different availability zones as well. The third point that we have here is cluster volume. So if it's a volume, then you are aware that the data that you have is stored on these volumes, and copies of the data are stored across availability zones within the region, and it is automatically replicated. So it's a good thing for you. Now let us set up the environment for our Neptune, and let's see how we can connect to Amazon Neptune from clients outside of the VPC using AWS Network Load Balancer. So let's bring up our VPC, that is our playing ground. And here are the two availability zones and our public subnet, which will hold the components that we want to create. So here we are aiming at running our design in at least two subnets in two availability zones, with each subnet in a different availability zone. That is our point number one. Point two here is that we want is to have our Neptune database subnet group to range at least two subnets in the two availability zones that we have. Okay, so it's ranging from two availability zone or two subnet groups that we have. So now that we have point one and point two ready, now it's time for us to create our network load balancer, and the external connections that we have will terminate to this. So once you get the request, your network load balancer points the request to the primary instance via the Neptune database cluster endpoint that you see at number 4 or point 4. Next, if there is any change to the cluster endpoint IP and other configurations, then it is handled by the Lambda function that we have here, and it makes the changes to the network load balancer. But how can we detect if there is any change? Yes, by using a CloudWatch trigger, which can invoke the Lambda function like this. Okay, so this is the basic idea on how it works. So let's take a recap. For replication, set up the cluster subnet group across more than one availability zone. Create your network load balancer and set the target to your network cluster endpoint or network cluster IP endpoint so that the users can connect to them by reaching out to the NLB or the network load balancer. Post which, for IP management and change management, plays a Lambda function that can make changes to the NLB so that you have the proper endpoint in place for connectivity. And then to detect the changes, place a trigger using CloudWatch. So if there is any changes to the primary IP address that we have, it actually makes the changes to the network load balancer. So if you get some time today while watching this, please try this setup and let me know how it works for you. I'll do a demo separately on this one, but you also can try this in meantime. Now let's talk about a few takeaways for the Amazon Neptune that we have. So the first thing is speed. The graph database like Neptune can query relationships between billions of vertices without bogging down, and this is a very good line by Amazon. So Amazon Neptune engine is optimized for storing billions of relationships and querying the graph with millisecond latency. So you are dealing with a service that can capture or query data, and not small amount of data. They are events and relationships, and it queries them for you in milliseconds. And in your exam, if you find a question related to graph databases, you know what to choose. Yes, that should be Amazon Neptune. So the second thing that we have here is replication and availability. Your table data is replicated automatically as Neptune replicates 6 copies of your data across 3 availability zones. So it provides us with high availability with replicas or treat replicas for the data that we have. That is, your table data is replicated automatically as Neptune replicates 6 copies of your data across 3 availability zones. So remember that, and remember that it is fully managed by AWS. And the third takeaway for us here is that Neptune makes it easy for the developers and decision makers as it supports graph query languages and data models like Apache Tinkerpop, Gremlin, W3C's SparkQL. And last but not the least, the use cases that we have for Neptune, so that can be used in recommendation engines, fraud detection, knowledge graphs, drug discovery, and network security as well. And there are so many other use cases to this. So mostly you may not know that we are using graph databases until and unless you actually try and think of the use case that it can help with. So keep thinking, keep understanding, and keep trying to innovate things on your way and try different things in a way that don't just stick to normal relationship databases. Okay, so that's all for Neptune databases. Let's move on. So now that we have discussed the top row of databases, let's start off with the next one, that is Document DB. So welcome to Amazon Document DB. So Amazon Document DB is an enterprise-ready document database service that scales JSON workloads with ease with MongoDB compatibility. So it would be apt on our part to start off by understanding how does a document DB work and what is a document DB and why MongoDB is mentioned here. So I know most of you might be already aware of these things, but let's talk about them for better context. So Amazon Document DB with MongoDB compatibility is a database service that is purpose-built for JSON data management at scale. This is fully managed and integrated with AWS and enterprise ready with high durability. Okay, so there is a lot of stuff that Document DB does, and we'll talk about them. So with Amazon Document DB, as it is fully managed service, you don't need to worry about the database management tasks such as hardware provisioning, patching, backups, or scaling. And the best part, as with other managed databases, is that it takes backup of your cloud database to Amazon S3. And it also provides point-in-time recovery, and that too up to the second for the last 35 days. So in any case, if you have a problem, your data will be with you. And that's a huge advantage when it comes to data integrity. So let's talk about some of the important pointers that will be very helpful for you. So the storage on Document DB scales automatically up to 64 terabyte without any impact, but you pay for only what you use. So that's a very good thing. It also supports millions of requests per second up to 15 low latency read replicas, and that too in minutes. And Document DB is designed for 99.99% availability and replicates 6 copies of your data across 3 availability zones. And as I already told you, it automatically and continuously monitors and backs up your cloud database to Amazon S3. And it enables point-in-time recovery up to the second for the last 35 days. And when it comes to us developers and architects, we have an advantage with integration as it implements the Apache 2.0 open source MongoDB 3.6 and 4.0 APIs. Now let's talk about why it's associated with MongoDB and how we can migrate our MongoDB workload to AWS Document DB. But before that, if you're not aware of MongoDB, you should understand that MongoDB is a source available cross-platform document-oriented database program or document database. So you need to understand here that open source and source available is different. So as I told you, like MongoDB is a source available cross-platform document-oriented database program. And you need to understand that open source and source available is a bit different. And you might ask me how. So if there is a software and the source is distributed along with that, it can be called a source available for you. So that is more about reading and viewing or modifying the source that is available along with the software. but not necessarily that you're going to contribute to that application, because you may read or view or edit it on your own for your own requirements. But the question would arise if you can contribute to the application community, which is the case when it comes to open sources. So that's the major difference that you have. And MongoDB is a NoSQL database that uses JSON-like documents with optional schemas. So that's the reason why it's set to have a MongoDB compatibility. So if you're using MongoDB for your current platform, then you have a very good option available to you on AWS. Now coming back to migrating MongoDB workloads to AWS, you have your source as MongoDB endpoint. And by making use of the AWS Data Migration Service or Database Migration Service, you can transpose the data that you have onto the target, that is your Amazon Document DB. So the source is the self-managed MongoDB database. Then you can parse it or transpose it using the Database Migration Service onto the target, that is the Document DB that is on the cloud. So now let's talk about the MongoDB and let's understand how we use MongoDB, but not exactly in depth, but to give you an overall idea of how things work here. So as you can see, we have our document that is JSON, so that we want to work on. So our main objective is to consider that this data or this document as a whole as an object that we will read, write, or update or delete. And this is also called a record, or this is actually called a record. And that is, a record in MongoDB is a document which is a data structure composed of field and value pairs. So just like in the JSON that you have, we have key value pairs. Here also in the document, we have the same. So we have the field as name, the value as John. We have a field called age. We have the value as 23. And we have the field as profession, and we have the value as engineer. So similarly, you have the key value pairs. And this is basically your record. So a record in MongoDB is a document which is a data structure composed of field and value pairs. And in MongoDB, we can create a database. And once we create the database, we can use Mongo shell to connect to the database by typing use database command, and the place where we store the data is called a collection. That is like your table in a relational database. In addition to collections, we have read-only views and on-demand materialized views in MongoDB, which we will discuss later. But coming back to collections, we can create collections by using the command db.collectionName.insert1 or create index and provide the record that we want to insert. So here, if the collection does not exist, MongoDB will create the collection for you. So if you see, we have db.myCollection, that is a collection name, .insert1 of the record that I have given. And here, if this collection does not exist, then MongoDB is going to create this collection. Okay. So let's see this collection here. We have the collection as my collection, and we have the record that we want to insert. And each of them is a key value pair. And once you executed this command on the Mongo shell, you get the output as acknowledged : true, and inserted ID is the object ID that you get. So you get the UUID as the object ID that has been created. And once you change or modify the record, the ID will change for you to identify changes that have been taken place. Okay, so you can see db.myuser. My users is basically the collection name .insert1 of the record. So this is basically the whole record that we have inserted: name, age, profession, and country. So once I have given this command and I have executed this, I get the acknowledgement that this is successful. And here the acknowledgement will be true, and the insert ID will be given to us in the form of the UUID. And you can see that if you are working on a document and this structure that is similar to the JSON, or it is basically the JSON document, so that is why you are going to call this as a type of document database, because we are working with the document itself. So now that we have seen how we can insert the data and create the collection, let's see how we can read the data. So we have read operation db.collection.find, by using which we can fetch the data as per our requirement. So if you see the first example here, so db.myusers.find, so db.thecollectionname.find, and I'm giving here the age. And so what we are trying to do here is we are trying to find the users whose age is greater than 20, and we want to have a limit of 5 entries. So what happens here is I have given the parameter that I want, or the field that I want, : and the condition that I'm going to provide here is the dollar greater than symbol or $GT that specifies that, or that denotes that it is the greater than symbol, and the value that it is having is 20. So I can write it like age colon dollar GT colon 20, which is the condition for age is greater than 20. So once I have executed this, I got the value like age is 23 for John. So we got the value for this, or we got the record here for that particular collection. And similarly, we have a condition where I can write a query as a string. So here, if you see db.myuser.find, and I have given country colon Australia. So this is my condition. So wherever in the record, if the field is country and the value is Australia, it should return me the value. So once you execute this, you will get the desired record. So Josh is one of the users who is of age 22 and is from country Australia. So this is how I can find. But you might ask how we can insert a new record. So if I have to insert a new record, I can do the same way. So like, let's create one more object document. So I can do a db.myCollection, or sorry, the collection name .insert1 again, and I can add a user or the document like Josh 22 Software Australia. And let's suppose I use the find command again to find all the users who have the age greater than 20, and I can limit them to 5. I'll get both the users. So you can see John and Josh. Basically this should be the second step, but it's okay. So that's what I wanted to show you. Like, yeah, if suppose you try to find the users based on a condition, you will get that. And here as well, once you make the insert, you will get the object ID. I just did not show it here, but you will be getting the acknowledgement and the object ID as well. And once you run this find command, you will get the result as you want. Now that we have seen one record at a time, let's see how we can insert multiple records at the same time. And here we can do that by using insert many. So if you see, we have 3 records like Josh, Jack, and Rahul. And you can provide insert many like db.myCollection or collection.insert many. And within this, you can provide a list of the records that you want. So there are 3 records within the list. And here, once I've executed them, then I get the acknowledgement equal to true, and I'll get the 3 insert IDs because they are inserted along with each other. So this is like a collection of inserts. So I'll get 3 object IDs for each of the record. So I hope it was clear. So now that we have seen insert, insert many, and read, let's check the update part. So here, if I wish to update the records, I can make use of the update commands or the update functionality that I have. So you can see we have update 1, update many, and replace 1. So let's suppose I want to update many. So what I can do is I can write the command in such a way that db.collection.update many, and I can provide the condition where age is greater than 20, and I'm going to see, or I'm going to add another parameter which actually sets a particular field value. So if I give $set, then it takes the parameter of the particular field, that is profession, and it is going to change the value to DevOps. So this condition actually tells us that for every user who has the age greater than 20, then change the profession to DevOps. And once you execute that, you will get the acknowledgement equal to true. And if suppose the conditions are satisfied, so you'll get the acknowledgement equal to true, inserted ID equal to null, because this is update statement. And match condition that you have here is count 4, modified count 4. Matched is like if it satisfies the requirement and it has a matching value that it gets, then it'll increase the count and it'll give you the count of the total values that it has matched and the value that it has modified. So if suppose it is like age is greater than 20, so out of 10, if suppose 5 have the age as 20, then it will give you like match count equal to 5. And if suppose the profession, if suppose it has a profession, then it will change it to DevOps. So if you can see here, once it has changed, so profession is now DevOps, and all the 3 entries that you have the age greater than 20. So now we have reached to a point where we can talk about delete. So here as well, we have the delete operations like delete 1 and delete many. So let's suppose I want to delete all the records with key whose profession is DevOps. Then I can use this db.collection or my collection name .delete many of the condition that I want to write is profession : DevOps. So if suppose the profession is DevOps in any of the records, then please delete them. So once I execute this statement, then it gives the acknowledgement as true and delete count equal to 4, because there were records and there were 4 records whose profession was DevOps. Okay, so what do we have here? So this is a minor comparison of how we place relational databases and MongoDB. So tables and relational databases are collections in MongoDB. Same way, rows on relational database is documents in MongoDB, and columns here are represented as fields in the MongoDB or MongoDB database. So I hope you got the point. So table in RDBMS is collection. So imagine in that way, and rows are basically documents and columns are basically fields. So I hope you got an idea on how things work here. Let's move on. So now let's talk about redundancy and data availability in MongoDB. And my idea here is that if you know these things, then it will be very easy for you to understand when you go for designing applications using Amazon Document DB. So if you feel you're already aware of these things and it is a bit boring, then also please stick around. It will be a refresher for you. When it comes to replication or data availability, the term replica set is very important. So a replica set is a group of MongoDB processes that maintains the same data set. As we know what replication is, here as well you have data on multiple database instance servers, and it provides you fault tolerance if one or more servers do not respond. So how does MongoDB handle replications? So you have your application with the driver to connect to MongoDB, and the primary node that you see here is the one that is going to be receiving the write requests. And once the MongoDB sends the write to primary, the operation is recorded in the op log. So op log or operational log is also a collection which stores the operations that take place on the database. And the secondary nodes that you see here replicate the op logs or the logs that you have, and these apply the operation that are being made to the dataset. So this is a 3-tier, and all the write operations are taken by the primary node, and the secondaries actually apply them to the dataset. So that was for write operations. You might ask, what about read? So here all members in the replica set can perform read operations. So you might say the read operation is going to primary in this diagram. So the reason is that by default it will get redirected to the primary itself. But as a client, you can specify the read preference. So it's something that you can choose from. So we learned about replications. Now let's understand how the secondary replica set behaves. Because as you can see, we have replications on both sides, and these both are secondary. So we need to understand how they are basically communicating or how they basically behave. So as you know, all the write operations are going to the primary, and the secondary actually replicates the primary's op log and applies the operations to the dataset. So the obvious question that comes up is that what happens if the primary gets knocked out or does not respond? So what happens to the write operations and who is going to handle them if the primary fails is one of your major questions. And this can only be handled, and this can only happen in a way as they talk to each other, or how we can monitor the health of the instances. So you can see we have mentioned heartbeat. So what is a heartbeat? So heartbeat is a process that identifies the current state of a MongoDB node in a replica set. And why is it called a heartbeat? It's because the replica set nodes send pings to each other every 2 seconds. So if MongoDB finds out if the primary is not responding, then MongoDB automatically switches the secondary to become the primary. And that's how it does it. But the main question would arise again is, how does it do that? And how is it doing that? How does it automatically switch a secondary to become the primary? What are the criteria here? Now you see what happens here. We know what's primary and what is secondary. Let's suppose the primary fails. The replica set that you have starts an election to choose which of the secondaries become the new primary. So once the timeout set for the primary fails, it creates a trigger, and that trigger tells MongoDB secondaries to elect one from the secondary to become the primary, like this. And this is how it manages automated failures. I know what you might be feeling, and yes, that's true. The replica set cannot process write information or write process or write operations until the election completes successfully. And the way they select the primary is based on which secondary has the highest priority value and which have more votes. And based on that, they select the primary. But in some cases, you may not be able to have a lot of replica nodes. So imagine that case study. So imagine that in this scenario, if you have one primary and one replica, then how will you choose the secondary? How do we vote? So if the primary fails, you have one replica, that is a secondary. So how are you going to vote then? And that is where there is a very important or interesting thing that we can discuss. So here is the interesting thing. So here what we can do is we can make use of an arbiter. And what this arbiter is, it's just like a friend who will vote for you. But wait, listen to me first. In this situation, we add an arbiter to your replica set. Imagine this to be a node, but an arbiter does not have a copy of the dataset and cannot become a primary. So remember these two things very carefully. So the arbiter can be your friend, can vote for you, but it cannot have a dataset or copy of the dataset and cannot become a primary. So even though it can't be a replica and can't be a primary, it can still help you. It will help you by participating in the elections for primary. An arbiter has exactly one election vote. So if it has one election vote, it can vote for the only secondary it has. So let's suppose this primary fails, the arbiter has only one vote and it can vote for this secondary. So then in this case, you can work with one primary and one secondary as well. And that's how it works. But as we discussed about how we can use primary and secondary, then how do we store data across the nodes? That's one thing that we need to talk about. And that's where we need to talk about sharding. And we need to understand what exactly is sharding. So sharding is a method for distributing data across multiple machines. In cloud terms, you can call this horizontal scaling. So here with sharding, you can add more nodes to support the growing demands of read and write operations. So if you see here, let us start from the bottom. So if you see, we have the shards here, and these are the replicas that you have that help you to store the data that you want and provide you with the high availability and data consistency. And with sharding, you add more nodes to support the growing needs of your read and write operations. On top, if you see, we have the application. We have something called the routers or Mongos. So these Mongos actually act like a query router and provide the interface between the client application and the sharded cluster. So as a query router, it helps you to route the query operations that you have. And when it comes to managing the configuration or the configuration settings of the cluster, you make use of the config servers. So the config servers actually stores metadata and configuration settings for the cluster. You can have one as well, and for better resilience in production, we can make use of up to 3 config servers. But there is one thing that we already discussed, that on MongoDB, the data that you have is stored or represented as a part of collections. And how does it store them and how does it get routed to the shards is basically with the help of the query router. Your data on MongoDB is stored as a representation of collection, and the way it actually stores them and how it actually gets routed to the shards is basically with the help of the query router. But how does it actually do that, or how does it actually look like? So let's check that out. So there is one more important point that you need to understand is with MongoDB, you have both sharded and unsharded collections. And we will talk about how it works. But first, let's start off with the design here. So you have your application you want to read and write, so with which you want to read and write. So here we have the Mongos or the routers, and let's bring up the 2 shards that we have, and we want to write and read the data from. So one thing that you need to understand is that sharded collections are partitioned and distributed across the shards in a cluster, and unsharded collections are stored on the primary shard itself. And each database has its own primary shard. So let's see the sharded collection. So this is the collection 1, and we have the sharded collection. So this is how it actually looks like. And then we have the unsharded collection, that is collection 2. So as you can see, the collections are partitioned and distributed across the shards in the cluster, that is collection 1. And collection 2 is the unsharded collection. So here we need to talk about a few important concepts that will help you understand the things better. So the first one is shard keys. So shard key is the way we shard a collection. That is, as mentioned here, MongoDB uses the shard key to distribute the collections or documents across shards. So the way it does is by creating the sharding using the MongoSH method called sh.shardCollection to shard a collection by using the parameters such as key and namespace. So the namespace that you have tells you which collection you are pointing at, and the key that you have tells you how you want to shard this collection. So here as well we have two values. The two values are 1 and hashed. So 1, actually if you give 1, then it tells us that the shard is range based sharding, and if you give hashed, then it indicates that it is a hashed sharding. So these are the type of shardings that you have, and you can read more about them. The second one is the shard index key. So if you have a sharded collection, then you need to know which record is at which shard, isn't it? So you don't know, then it will be very hard to find. So for that to identify that, we need something called an index. So all sharded collection must have an index that supports the sharded key, and this can be done by using the same shard collection method. So here if you don't have the index, it will create the index on the shard key. So that's a very good way to identify the data that you have on the collections and the shards. Third one is chunks, where MongoDB partitions shared data into chunks. So it takes a subset, or it takes in a subset of sharded data and helps it to get stored in chunks in the shards. And the last one that we have is a sharded cluster balancer. So just now we spoke about chunks, isn't it? But for it to balance the amount of chunks in each shard, we make use of the sharded cluster balancer. So the MongoDB balancer is a background process that monitors the number of chunks in each shard. So that is how it is able to balance the number of, or the amount of chunks that we have in each shard. Okay, so these 4 points are very important, so you can remember them: shard keys, shard key index, chunk, and sharded cluster balancer. So now that you have some idea about MongoDB, you are ready to think on the lines of designing your applications with AWS using DocumentDB. And this is how you might work when it comes to using DocumentDB. So let's suppose you're making use of the Amazon Guard Duty or Amazon Translate or Transcribe. Mostly with the APIs that you consume, you will get the response as JSON. That could also be used as your source of the data that you want to process or store as a part of your DocumentDB. And then you might use services such as Lambda, EKS, ECS, EC2 to model your data so that it can be used in IoT, gaming data. And you can also use them for your log processing and storage, and also for your time series data. And once you have stored them in your DocumentDB, you can query the JSON data in its natural form without translation, and which enables developers to iterate faster and be more productive. So that's a very good thing. So source is JSON data, you can model them and you can store it and consume it in its raw form or natural format. So now let's talk more about what you need to keep in mind while making use of Amazon DocumentDB. For us to start working with DocumentDB, the first thing that we need to do is begin by creating a cluster. So you need to imagine instances of the cluster to be the database instances. And a cluster contains or consists of 0 or more database instances. And you have the cluster volume that manages the data for those instances. So remember this very carefully. Instances of the cluster, imagine them to be the database instances. The cluster consists of 0 or more database instances, and you have the cluster volume that manages the data of those instances. So the cluster volume is the virtual database or virtual storage volume that is spread across multiple availability zones. The best thing is that with virtual database storage volumes, you have the option to scale on demand, because you need to just attach them and they work in conjunction with each other. And talking about the cluster, we need to remember a few points here. So a cluster consists of 0 to 16 instances and a cluster storage volume that manages the data of those instances. And the primary instance that you see here are responsible for all the writes, but for the reads, the primary and replicas are responsible, both of them. And when we talk about the data is stored in the cluster volume, which is having copies in 3 different availability zones. And don't worry, each availability zone will have its copy of the cluster data. So if you see here, we have 2 sections. One is compute and one is storage. So let's start off with the compute first. So you see 2 things here, the primary and the replicas. So as I already told you before, the primary endpoint that you have supports read and write operations. Remember, primary supports both read and write, but it is responsible for all the writes, as it performs all the data modifications or on the cluster volume. And each Amazon Document DB cluster has one primary instance. And moving on to the replicas, you already know that replicas support only read operations, and the cluster can have up to 15 replicas in addition to the primary instance. So it is 15 replicas with one primary, so total of 16. That's the maximum that you can get. So you might ask me, why do you need more replicas? So imagine a situation where you have a lot of traffic and a lot of demand. How will you process the read queries? You can manage it with the primary for write, but for read, you need more replica instances whose task is to give you the data based on your queries that you have. So having multiple replicas enables you to distribute read workloads. In addition, by placing replicas in separate availability zones, you also increase your cluster availability. That's a very important point. And even though AZ fails, you still have an option to bounce back because you have the high availability in place. And here the instances you have provides you the processing power for the database, which will help you in writing data and reading data from the cluster volume or the cluster storage volume that you have. And as I already told you, the cluster can have 0 to 16 instances. So these are the way like it has been distributed. If you see the distributed storage volume, so even if it is available in 3 availability zones, it has the data set of the cluster replicated across the 3 availability zones. So now let's come back to the storage. So here Document DB cluster uses cloud native storage service to replicate data 6-way across 3 availability zones. And the best part here is that it uses cloud native storage because it's built for the cloud, as it will scale out when the demand increases and has fault tolerance in place, and it is optimized for the cloud. So it's a very good thing. And this solution here provides high durability and available storage. And here we have exactly one cluster volume, so which can store up to 64 terabyte of data. So I hope you got the points here. Let's move on. So now that we know how things work, let's talk about some of the important pointers that you need to remember for the exam. So here the storage volume that we discussed actually grows in increments of 10 GB up to the maximum of 64 terabytes, and that is spread across multiple AZs. So you can support high volume application request by creating up to 15 replica instances. So this is actually 0 to 16, including the primary. And it runs in Amazon VPC, so you can isolate your database in your own virtual network. The next one is when it comes to handling failures. If an instance fails, the Amazon Document DB automatically restarts the instances and associated processes. And it also has automated failover to one of up to 15 Amazon Document DB replicas that you create in other availability zones. So that's a very good thing. And here you get an automatic backup retention period of up to 35 days. So you can have a restore point to replenish the data that you have lost. And when it comes to data encryption, you can do that by encrypting your database using keys that you create and control through AWS Key Management Service or KMS. The next one is supported instance classes. This is very important for you to know. This supports R4, R5 and T3. So this is also based on the region that you have. So R4, R5 and T3. And when it comes to monitoring your database or Document DB, you can make use of the AWS CloudWatch and CloudTrail for the Document DB API calls. And this is like very common because for security, mostly you use Key Management Service, and for monitoring, it's obviously CloudWatch and CloudTrail. And when it comes to connection endpoints, you can make use of the AWS Management Console. So connection endpoints in the sense like how we are able to connect to this. So you can make use of Amazon Management Console or by using AWS CLI, or the third one is Mongo Shell 4.0. So you can use all 3 of them to connect to your Document DB. So Amazon Document DB is also compatible with MongoDB 3.6 and 4.0. So that's a very good thing as well. Now that we know the pointers, let's talk about how we can create the connection endpoints and access the Document DB cluster as a user. So that's a very interesting thing. Let's go check that out. So let's talk about how our users can migrate to AWS Document DB from on-premise locations, and that's what we are going to discuss now. So this is the customer side on-premise location where we have the database, which is using MongoDB as a source, and the customer application. So this everything becomes the source for our document database. As I already told you in the beginning of the session, for migration of MongoDB from source to AWS Cloud, we make use of the AWS Database Migration Service so that it can help us to transform the data that we have from our source to the Document DB, that is our target. So here we have placed our migration task at the public subnet and thus will act as our migration or AWS DMS replication instance and will help with the replication. Next is for us to have the migration instance. So it will help us dump the data that we have, and it will help us increase the number of parallel connections. So for now, the AWS cloud side is done. The next thing is about connecting both the source and the target. And yes, the first option for us is to use the VPN connection from the on-premise, so we can connect the source to the target endpoint using this connection. And to make it more secure, we can enable encryption using KMS, and for encryption on flight, we can have TLS encryption in place. So this is one way of connecting MongoDB source to your target document DB cluster. And now there is another option that you can make use of, that is instead of using VPN, you can use the direct connect service. So having private connectivity using this as well. So instead of using the VPN connection, you can make use of the direct connection. So I hope you got some idea on how things work in simple terms, and this may be way too much information that you need for the exam, but for your experience or real-time experience or learning purpose, I hope it has helped you in this. And that's all for the document DB side. I hope you enjoyed it. Let's move on. So the first thing that you need to understand about Amazon Aurora is that it's a MySQL and PostgreSQL compatible relational database built for the cloud. And Amazon Aurora is up to 5 times faster than standard MySQL databases and 3 times faster than standard PostgreSQL databases. And it provides the security, availability, and reliability of commercial databases at 1/10 the cost of the traditional databases. So the major differences here with Amazon Aurora is that Amazon Aurora is fully managed by Amazon's RDS, or the Relational Database Service, which automates the time-consuming administration tasks that we have, like hardware provisioning, which we all know, like server racks and basic hardware that we provision, the database setup like installation, patching. So it involves like which version is secure and compatible, and it helps with the backup as well for your data, as you saw with classic RDS. So the major advantage that you and your customers and clients have is that the Amazon Aurora features a distributed, fault-tolerant, self-healing storage system that auto-scales up to 64 terabyte per database instance. And when it comes to performance, Amazon Aurora delivers high performance and availability with up to 15 low latency read replicas. Second is the point-in-time recovery. So let's suppose you want your data that was backed up like 6 days back, you can do that as well. Third is the continuous backup that you get as your snapshots get uploaded to Amazon S3. And last but not the least is replication across 3 availability zones. So this was a brief introduction to the Amazon Aurora database. Let's move on. So let's see the benefits of using Amazon Aurora. So the first point that we have here is high performance and scalability. So you get up to 5 times the throughput of standard MySQL and 3 times the throughput of standard PostgreSQL databases. You get a budget price at about 1/10 the cost that we already discussed. You can easily scale your database deployment up and down from smaller to larger instance types as your need changes. To scale read capacity and performance, you can add up to 15 low latency read replicas across 3 availability zones. And Amazon Aurora, as we already discussed, automatically grows your storage when you need them up to 64 terabyte per database instance. Wonderful, isn't it? And the next one that we have here is high availability and durability. So Amazon Aurora is designed to offer greater than 99.99% availability, replicating 6 copies of your data across 3 availability zones and backing up your data continuously to Amazon S3. With global database that we have, a single Aurora database can span multiple AWS regions to enable fast local reads and quick disaster recovery. So third point that we have here is highly secure. Yes, security is very much important. So security in Aurora actually includes network isolations using Amazon VPC, and encryption at rest using keys you create and control through AWS Key Management Service, that is a KMS, and encryption of data in transit using SSL. On an encrypted Amazon Aurora instance, data in the underlying storage is encrypted, as are the automated backups, snapshots, and replicas in the same cluster. So if your Amazon Aurora instance is encrypted, the data that you have on the storage will also be encrypted, as well as your backups, snapshots, and replicas also will be encrypted in the same cluster. So the fourth point is that we have for us is MySQL and PostgreSQL compatible. So if you already have a MySQL or PostgreSQL database, you can easily migrate your MySQL or PostgreSQL databases to Aurora using the standard MySQL or PostgreSQL import export tools and snapshots actually. So fully managed. So this is one of the beautiful features that moving into cloud with AWS, we get it. So Amazon Aurora is fully managed by Amazon RDS. So you no longer need to worry about the database management tasks such as hardware provisioning, software patching, setup, configurations, or backup. And Amazon Aurora automatically and continuously monitors and backs up your database to Amazon S3. With that, you get a point-in-time recovery as well. So you can monitor your database performance using Amazon CloudWatch. Mostly, the exam might ask you about monitoring, and you must remember that monitoring techniques involve mostly about Amazon CloudWatch and enhanced monitoring and performance insights. So as you now know why people are crazy about AWS Aurora, let's check how it actually works. So this is a very interesting part and very important for the exam as well. Let's talk about how the read replica and high availability works for Amazon Aurora database. So for high availability, we must ensure we have our Aurora database set up across multiple availability zones. That probably is the first thing we need when we talk about availability. So in hindsight, you should remember that Amazon Aurora is designed to offer greater than 99.99% availability, replicating 6 copies of your data across 3 availability zones and backing up your data continuously to Amazon S3. So let's bring up our 3 AZs. So we have our 3 availability zones, AP South 1A, AP South 1B, and AP South 1C. So here we have the data that we wish to store on the Aurora database, regardless of what database it is. Either it can be a MySQL or PostgreSQL. Don't get confused with the database service and the engine. Aurora provisions a service to house your database engine. So as we have our AZ ready, the data replication enabled, which we call shared data or storage volume replications. So Amazon Aurora stores 6 copies of your data across 3 availability zones, isn't it? And the storage is basically stripped across multiple volumes. Let's see this in action. So as you see, our data is being copied across 3 availability zones and they are being replicated across multiple instances. Let us wait for our data to be replicated. Okay. Coming back to the Amazon Aurora primary instance, you get a master endpoint for writing the data to the database. And remember, it needs 4 copies out of 6 to write. And you get a read replica, which needs 3 copies out of 6 to read. So let's bring up our read replicas in other availability zones as well. Wonderful, isn't it? So be assured, if there is a problem, the master node that you have here will auto failover in just or less than 30 seconds. So it's a beautiful thing to have. And you also get the master along with 15 other read replicas for your read operations. So master plus 15 other read replicas. And one of the best thing is that you get cross-region replications. So if your database is in some other region, you will find your data being replicated there as well. So I hope you got this right. Remember that Amazon Aurora stores 6 copies of your data across 3 availability zones, and the storage is basically stripped across multiple volumes. You will get a master endpoint for writing the data to the database, and remember, it needs 4 copies out of 6 to write. And you get a read replica which needs 3 copies out of 6 to read, and also the master along with 15 other read replicas for your read operations, thus making your database highly available. If everything is set, then let's move on. So now let's discuss on the architecture for Aurora client and its interaction to the Aurora cluster. So as we know that the shared volume read replicas, we can have auto scale from up to 10 GB to 64 terabytes per instance. Remember, in Aurora, you get the master node or the DNS, which you can use to write the data, which, as you may know, can fail. And upon failover, what happens? The DNS changes. And if the DNS changes upon failover of the master, as it self-heals, AWS creates a new one to make sure that your write operations run smoothly. And for that, RDS provides you a write endpoint.
Yes, a write endpoint or the DNS name, which always points to the master even if there is a failover. In this way, RDS knows where the master is in case the client wants to write to the database. Next, listen to this very carefully. I already told you can create read replicas, and remember they can auto scale up to 15 read replica instances. This is awesome. But when we speak about auto scaling, we know the instances are bound to topple or fail. Then how will the client or application know how to connect to the read replicas? For this, RDS provides a reader endpoint which also acts as a load balancer and ensures you have accurate read endpoints ready to be consumed when you need them. It connects to all the read replicas and does the job for you to remember where your read replicas are. I hope you will remember all this. If you have any confusions, post the queries in the comment section below and we'll sort them out. So if everything is fine, let's move on. So it's time now to discuss a new offering by Aurora that's called the Aurora Serverless. So what you need to remember here is Amazon Aurora Serverless is an on-demand auto-scaling configuration for Amazon Aurora, which is basically MySQL compatible and PostgreSQL compatible, where the database will automatically start up, shut down, and scale capacity up or down based on your application needs. And it enables you to run your database in the cloud without managing any database instances. So serverless means you don't manage most of the tasks that you would with the traditional Aurora, and you simply create a database endpoint, optionally specify the desired capacity that you have, database capacity that you have, the range that you have, and connect your applications to that. And serverless mostly gives the cost benefits where you pay on a per second basis for the database capacity you use when the database is active. So no capacity planning is needed for these serverless databases. So when we visualize, see this, we have our client and it wants to access the Aurora database. And like previous explanations, we have our shared scaling for volumes, and for the client to connect to the AWS Aurora, connect to the proxy fleet, which then redirects the request to the Amazon Aurora. I hope you remember the RDS proxy that I mentioned in my last session for AWS RDS. Remember, with Aurora Serverless, the database endpoint connects to a proxy fleet that routes the workload to a fleet of resources that are automatically scaled. Because of the proxy fleet, connections are continuous as Aurora Serverless scales the resources automatically based on the minimum and maximum capacity specifications. Here also, you can see with the increase in demand, it scales automatically and we don't need to change or configure anything. That's the beauty of Aurora Serverless. And here you don't need to worry about the modifications you need to make, or if you need to change your application to use proxy fleet, Aurora Serverless manages the connections automatically. So let us go over the points that I carefully mentioned here as well. So for the first point that we have here is it removes the complexity of managing database instances and capacity. The second point that we have here, the database will automatically start up, shut down, and scale to match your application's needs. So that is very nice. And it seamlessly scales compute and memory capacity as needed with no disruption to the client connections. And it gives you the pay only for the database resources you consume on a per second basis. And it is built on distributed fault tolerant self-healing Aurora storage with 6-way replication to protect against data loss. So I hope you won't be forgetting the points that I have made here. If you feel you missed out on something, watch the video again so that you can grasp everything that I mentioned here. It's really important for the exam. So now we have discussed Aurora for multi-AZ, RDS for multi-AZ, single region, and serverless as well. So let's discuss Aurora Global Database then. So Amazon Aurora Global Database is designed for globally distributed applications, allowing a single Amazon Aurora database to span across multiple AWS regions. So what it means is you can have your database across multiple geographical locations. For example, if you have a database at Mumbai, that is Asia, you can have the same in Oregon, that is in USA. So you might say, how is that possible? The same database thousands of miles apart, will it be able to perform accurately or same as the ones that are close to us? I'll say yes, it will be. AWS Aurora Global Database replicates your data with no impact on database performance. enables fast local reads and with low latency in each region, and provides disaster recovery from region-wide outages. And global database uses storage-based replications with typical latency of less than 1 second, using dedicated infrastructure that leaves your database fully available to serve application workloads. Even though there is an outage, it's less than 1 minute, and a secondary region will be up and running for your use. So before moving to the visual explanations, there are two features that we need to discuss here. The first point that we have here is sub-second data access in any region. So with all the overheads, you have the global database regardless of the number and the location of secondary regions. The typical cross-region replication latency is a mind-blowing below 1 second. That is why it's called sub-second data access in any region. And one more reason to awe upon the global database is that extending your database to additional regions has no impact on performance. The second one is the cross-region disaster recovery. As we discussed in the features above, if your primary region suffers a performance degradation or outage, you can promote one of the secondary region to take read or to write responsibilities. So no worries about the power failures or any other outage. Your application will always be available. So if you wish, you can promote one of your secondary regions to take up the responsibility for reading and writing. The next point is probably the most outstanding features I feel is that an Aurora cluster can recover in less than 1 minute, even in the event of a complete regional outage. So if the whole region has collapsed, also within 1 minute, you'll be up and running. That's very good. And for the business point of view, it provides your application with an effective recovery point objective, that is a RPO of 1 second, and a recovery time objective or RTO of less than 1 minute. Do you know what is the difference between RTO and RPO? And why it is important for the organization and the product and for you? If you don't, let's discuss this. So RPO, which is also known as recovery point objective, is basically the interval of time that might pass during an outage before the quantity of data lost during that period exceeds the threshold set by your organization. Lot of words, isn't it? So for example, let's suppose your company says all the data that has been backed up should be within the last 10 hours. So if there is an outage and your last restored data is from 8 hours back, then you're in a safe zone, which is basically your RPO. So when it comes to AWS Aurora Global Database, it has an RPO of 1 second. That's mind-numbing. And when it comes to RTO, or what we call as our recovery time objective, it is a target time you set for the recovery of your data and infrastructure after a disaster has struck. So for example, if your company says that your application can survive a failure time of, let's suppose, 10 minutes, then you need to ensure your data and infrastructure is up within the time limit. And when we see this in Aurora Global Databases, it's only 1 second. Let's visually see how it works. So we have our primary region US East 1, where we have our Aurora database, and we are doing just fine. But we wanted to support data to be available across another region, that is the US East 2, which is our secondary region or the secondary database that we have. Our primary region holds the master where we store the data, and with the cross-region application, it gets written to the other region, which we only use for reading. So in the first primary region that you have the provision to read and write, and you can create a secondary region as well where you have only read-only access. So let's go over the points once again. I just want you to remember that if you have your database and you want it to be set up in any other region apart from the region that you have, you can use Amazon Aurora Global Databases. So when we start going over the AWS documentation of Dynamo DB, the first thing that you read is Amazon Dynamo DB is a fast and flexible NoSQL database service for any scale. So we all know what fast and scalable means and what a database means. But when it comes to NoSQL, let's get some data on this. So I'm sure most of you have already used a NoSQL database like Cassandra or MongoDB, but I would just take a few minutes to explain this, as we will see the difference between them and the SQL database in brief. So when we speak of NoSQL, the first thing that you should understand is that NoSQL doesn't necessarily mean not SQL. It means not only SQL. or not just SQL. So the basic difference when people speak about NoSQL databases is that they say you cannot have a relationship between tables, and it is called a non-relational database. But it's not all true. Yes, you can create relations in NoSQL databases. I'm sure you know this if you have already worked on Cassandra. But having said that, the way the NoSQL database handles relationships is a bit different from the traditional databases, because they support SQL-like querying languages to extract data from the database. And more importantly, because NoSQL database don't necessarily adhere to the principles of ACID, which are the atomicity, consistency, isolation, and durability. So as I have already mentioned here in the slide as well, that NoSQL, that is the non-SQL or not only SQL database, store data in a format other than relational tables. So which can include documents, key value pairs, wide column data structure, and graphs as well. So what it says is, rather than storing in traditional relational tables, we have the flexibility of storing data in complex forms, such as key value pairs or documents or graphs as well. So let's see a visual representation of the offerings that are from these databases. Okay, so for the SQL, you could use the entity relational model or the entity relationship model, the table relationship model actually that we speak with databases like Postgres, MySQL, MS SQL, or Oracle. So next we have is our OLAP database, OLAP, which stands for Online Analytical Processing. So OLAP allows users to analyze database information from multiple database systems at one time, while relational databases are considered to be two-dimensional, and OLAP data is multidimensional, meaning the information can be compared in many different ways. So these are mostly used for data mining and huge online data processing for the relational data. And when it comes to NoSQL, we have a variety of solutions for us. We have the wide column, where you have a single huge column structure and you feed all the data in the single row, and you have mostly no relations involved. And next is the graph database. As you know, LinkedIn uses as well to have a connection between entities that can be used later for relationships. And the next one that we have here is the document database, which are mostly used to have a data storage for entities which can be termed as a document, but mostly encoded. So the encoding mostly that I use include XML or YAML files or JSON files and these type of data. And the very famous key value store, so which we have discussed before as well with Elasticache, which is mostly used for caching and storing simple data with a key and a value pair. So now, as we have seen all this, let's see what AWS has to offer. So for the relational database that you have, we have Amazon RDS. And for the OLAP, we have AWS Redshift, which actually is based on the PostgreSQL database. And for the key value pair, we have the Dynamo DB, which can be a replacement for the Elasticache. And the wide column also, we can have it with the Dynamo DB. And AWS Neptune, which provides us the flexibility to use graph database, and document DB as well, which is a primary intake that we have for AWS, which in the background uses MongoDB. So that is for the document store. Okay, so I hope this was clear. So let's move on then. So now I hope you might have a clear understanding of what NoSQL databases are. So we on this session won't be digging upon how and what are the differences, but you can surely read a lot about them for more information. So now let's move on to the Dynamo DB then. So Amazon Dynamo DB is a managed NoSQL database service. So Amazon Dynamo DB is a key value and document database that delivers single-digit millisecond performance at any scale. And as we know, it can act as a replacement for Elasticache, and it is known to provide sub-millisecond performance. That is, Elasticache is known to provide sub-millisecond performance. Dynamo DB is also not that far behind. It also gives you faster performance with single-digit millisecond performance. And DynamoDB is serverless with no servers to provision, patch, or manage, and no softwares to install as well, or maintain or operate, and that's a very good thing. And DynamoDB automatically scales tables up and down to adjust for capacity and maintain performance as well. And for resilience in DynamoDB, availability and fault tolerance are built in thus eliminating the need to architect your application for these capabilities. And this is very important because you should always remember what the service has to offer. And DynamoDB also provides both provisioned and on-demand capacity modes so that you can optimize costs by specifying capacity per workload or paying for only the resources you consume. And one more important thing is DynamoDB is a key value and document database that can support tables of virtually any size with horizontal scaling. And this enables DynamoDB to scale to more than 10 trillion requests per day with peaks greater than 20 million requests per second over petabytes of storage. And it provides automatic data replication over 3 availability zones in a single region. So you should remember that 3 availability zone, automatic data replication over 3 availability zone in a single region. Okay, and watch the video till the end. We have a very special visual explanation on this one as well. And for backups with DynamoDB, the data is securely backed up to S3. And when it comes to integration with other services, DynamoDB provides integration with Elastic MapReduce, the EMR, and the data pipelines and Kinesis as well. And for the security aspect, security and access controls can be applied using Amazon IAM services. So when it comes to consistency or read consistency, DynamoDB provides both strong and eventual consistency. So what does it mean? So let's suppose you have a table called employee in India. Let's suppose we have IP South 1 region, and in US, let's suppose we have US West 2, which is Oregon. So if you have the same table across regions, they are not considered to be same tables anymore. So it's not magic that the data will replicate across the region, or in case should also be available, replicated across multiple availability zones. For this, we need consistency, because with all the experience that we have with networking, we know with cloud, there comes latency. So remember this, eventual consistency means when you read data for a DynamoDB or when you read data from a DynamoDB, the response might not reflect the results of the recently completed write operations. The response might include some stale data. So if you repeat your read request for a short time, after a short time, the response should return the latest data. And with strong consistency, on the other hand, what happens there is when you request a strongly consistent read, DynamoDB returns a response with the most up-to-date data, reflecting the updates from all prior write operations that were successful. So, however, this consistency comes with some disadvantages. Okay, you might get the latest data every time, but there will be some disadvantages to it. So what are the disadvantages to it? So strong consistent reads may have a higher latency than the eventual consistency reads because it will take some time to gather all the information, so there will be latency. And strongly consistent reads are not supported on global secondary indexes, which we will discuss about this in a short while. And DynamoDB has 2 read-write capacity nodes for processing reads and writes on your table. So the first one that we have here is the on-demand, and the second one is the provisioned, which is default and which is free tier eligible also. Amazon DynamoDB On-Demand is a flexible billing option capable of serving thousands of requests per second without capacity planning. So if you choose provision mode, you specify the number of reads and writes per second that you require for your application, and you can choose auto scaling to adjust your table's provision capacity automatically in response to the traffic that you get. And Amazon DynamoDB stores data in partitions. Basically, a partition is an allocation of storage for a table backed by SSDs and automatically replicated across multiple availability zones within the region. And partition management is handled entirely by DynamoDB. You never have to manage partitioning yourself, and you get the pay-per-use model, and you never pay for hardware or services that you're actually not using. And for caching, this is very important. Remember this. Okay, so DynamoDB DAX is very important for the exam. So what DAX is, that it's a fully managed in-memory cache for DynamoDB. So which reduces DynamoDB response times from milliseconds to microseconds. And when in the exam, they ask what can help DynamoDB improve performance or latency by caching, please opt DAX, or what we also call as DynamoDB accelerators or Amazon DynamoDB accelerator. So as I already mentioned, that DynamoDB can be used as a key value database in place of Elasticache. So that also is provided to us with DynamoDB. And also you can enable CloudWatch monitoring with this for your logs and everything. And it also provides encryption at rest using KMS and in-flight encryption using SSL. So mostly in the exams, you must remember that whenever there is a question for like encryption at rest, mostly it will be KMS and encryption in flight will be SSL. Okay, so I hope this was clear. Let's move on to the next thing then. So let's get into some more details for Dynamo DB. So the data types that it supports are basically, there are three that I have mentioned here. One is a scalar, which basically consists of numbers, strings, binary, boolean, and null. The second one that we have here is a multi-valued, which is a string set, number set, binary set, and the document like list and map. And for the data model, it consists of three entities, or basically two mostly. So the tables, items, and attributes. And attributes are basically your key value pairs. And tables are, as the name tells you, your non-relational, mostly non-relational tables. And items, when you hear items with respect to DynamoDB, they are just rows. Okay, and they should contain a primary key based on which your DynamoDB creates partition and you access the data. Okay, so next, moving on to primary key. I told primary key, so the next thing will be primary key. So the primary key are just like in any other NoSQL database, must be unique so that it can find the exact item in the table. And there are two primary keys that you need to understand that they have. So the one is the simple primary key and another one is the composite primary key. And the simple one actually is similar to the standard key value stores like memcached and accessing rows in the SQL table by using the primary key. And the second one, the composite key, is basically you specify both a partition key and a sort key. Okay, sort key is used to sort the items in the same partition. So you need both the keys in the composite key. So both of them constitute a single key, which makes it as a composite primary key. And moving on to like LSI and GSI, it would be a bit high level to discuss in depth. We will have a separate video on this, and it is not that important for the exam as well. But you need to remember that LSI, local secondary index, uses the same partition key as the underlying table, but a different sort key to match the pattern to get the data. But GSI, on the other hand, that is the global security index, can define an entirely different primary key for a table. Okay, so there is a basic difference between both of them. And there are a couple of more important points that we need to remember for the exam as well, and for the understanding of DynamoDB. The first thing is obviously Amazon DynamoDB streams. So a DynamoDB stream is an ordered flow of information about changes to items in a DynamoDB table. So which basically is very important because they can be used for near real-time cross-region replications, which can move all the transactions that you have to another region so that they can create a replication over there. And we have already discussed the on-demand capacity mode before. And one more thing, or one more important thing, is that DynamoDB has a built-in support for ACID transactions, as we already discussed, and on-demand backup and point-in-time recovery as well for the data. I hope this was clear. So let's move on. So we have discussed all the things that make up for the DynamoDB. Let's see how it operates and what it has to offer. And the thing that we are discussing are very important for the exam. So keep up with me on this and let's begin. So most of the time as a solutions architect, mostly you will be asked about DynamoDB partitions and how does the availability work and how does the replication work. Amazon DynamoDB stores data in partitions. Okay, remember this. And a partition is the allocation of storage for the table, backed by the solid state drives, which is automatically replicated across multiple availability zones within the particular AWS region. Now let's see some drama here. So we have our AWS region A, and where we have hosted our DynamoDB database or the table. So when you create a table, the initial status of the table is creating, and during the phase, DynamoDB allocates sufficient partitions to the table so that it can handle your provision throughput requirements. You can begin writing and reading table data after the table status has changed to active. Okay, so remember that you can begin writing and reading data from the tables once the status has changed to active, from creating to active. Okay, and we have our 4 partitions here, and you read and write based on the consistency we set for our data query. Okay, so as we already discussed, that a partition is an allocation of storage for a table backed by SSDs and are automatically replicated across multiple availability zones within the region. It gets done with synchronous replication. So data across multiple partitions also gets replicated with synchronous replications. And let's move on to something that is really important. You want your transactions or data to be replicated to another region, right? So let's suppose region B. So we have DynamoDB streams now, as I already told you, to get near real-time cross-region replication. So using database streams or the Dynamo DB streams, you can basically have cross-region replication. So the data that you have on region 1 can be replicated across the region B. And if you need to have your data to be available across multiple regions, just like this, let's suppose we have region C and region D, then what we go for is Dynamo DB global tables. And that is done with async replications. So remember one thing very specifically here, and this is really important for the exam as well, because these are the few tiny things that are that will be asked in the exam. Okay, so you have your client that gets connected to the table that is in region A that has multiple partitions, and based on the consistency of the read and write, you basically write onto these partitions. And based on the table that you have, like you have multiple primary keys, then you will have multiple partitions to it. And based on that, the data is written on the SSD, which are being replicated with synchronous replication. And if you want your data to be having a cross-region replication, then you use Dynamo DB streams. And if you want to have your data replicated over multiple regions, then you can use global tables. So I hope this was clear. This is the only thing that you need if you want to just answer the questions on DynamoDB, because this is the whole gist of DynamoDB. When it comes to DynamoDB, as we discussed the importance of having partitions, we need to talk about how many partitions do we need, on what basis the partition value is calculated, or the number of partition values are calculated. So the read capacity mode controls how you are charged for read and write throughputs and how you manage capacity. So there are two terms here that you need to understand, that is the throughput and the size. Okay, and you can set the read write capacity mode when creating a table, and you can change it later as well. There are two things here, the number of partitions for throughput, and the other thing is the partition for size. So let's get to the first one. So the number of partitions, that is the throughput, let's term it as NPT, the read capacity unit for reads divided by 3000 RCU, that is the capacity threshold, plus the write capacity units, that is for the writes, divided by 1000 write capacity units. Okay, this is the number of partition for throughputs. Next one, number of partitions based on the terms of size. So the first thing that you need to understand is we will be dividing the table size in GB by 10 GB. And then number of partitions will be the max of NPT by NPS. Let's get our diary out. So let's suppose we have the number of partition that is for throughputs. Let's suppose 6000, that is for the RCU for reads, divided by 3000 plus 1000, that is for the RCU for writes, by 1000 WCU. And that comes as 3. And the number of partition in size will be 16. Let's suppose 16 GB for the total size in GB for the tables. So the next one that we have is the number of partition of size, that is the table size in GB, that is 16 GB, let's suppose, by 10 GB. So that is 1.6. And the max number of partitions will be the max of 3, 1.6, which is obviously 3. So this is the basic calculation that we do, or the DynamoDB does, to fetch you the number of partitions. Okay, so I hope this was cool enough, and we have done some mathematical calculations as well. So it's really a good thing to say at the start of the session that there might be a few tricky questions related to caching and Elasticache, and it could be joined with another service to make it more relevant. So something like your company is starting to use AWS to host new web applications. A new 2-tier application will be deployed that provides customers with access to data records. It is important that the application is highly responsive and retrieval times are optimized. You are looking for a persistent data store that can provide a required performance. What AWS service would you recommend for this requirement? So for the solutions architect exam, AWS always wants you to read big lengthy questions, not always, but half of the time, so that the time you reach to the end of the question, you forget what you have read in the top half. So Elasticache for AWS is a fully managed in-memory data store compatible with Redis or Memcached, and it powers real-time application with sub-millisecond latency. So if you already have used Redis or Memcached, you might know that what an in-memory data store is and how it works and what it is used for. So if you haven't, then let me tell you what in-memory data store means. So if you have used database before, databases are typically storage based, and they are supposed to be persistent, and they are stored on storage volumes. And on the other hand, in-memory databases are stored on volatile memory like RAM, which mostly is our main memory. And based on the computing knowledge we have, we all know that accessing the main memory is way faster than accessing your storage disk. And Elasticache falls into the category which uses the main memory, in turn, which is very, very fast. And there are two famous in-memory data stores that we have, the Redis and Memcache that I've already told you. And remember, just like we have Aurora RDS, which is for Postgres and MySQL, Elasticache is for Redis and Memcache. Okay, so the way we are able to create instances for Postgres and MySQL using Aurora or RDS, we can do the same for Redis and Memcache using Elasticache. Amazon Elasticache allows you to seamlessly set up, run, and scale these in-memory databases. So most important aspect of using Elasticache is that it boosts the performance of your existing databases by retrieving data from high throughput and low latency in-memory data stores. And you can make use of this for caching, session stores, gaming, geospatial services, real-time analytics, and queuing. And as it's an in-memory database, it gives you sub-millisecond response time. It is fast. Like when you think about sub-millisecond, it's less than a millisecond. And you know millisecond is 1,000th of a second. So it's very, very fast. Apparently faster than my first breakup. So jokes apart, I hope you get the idea, isn't it? So Amazon Elasticache has no upfront costs. You pay only for what you use. There is no minimum fee. With on-demand nodes, you pay only for the resources you consume by the hour without any long-term commitments as well. So with reserve nodes, you can make a low one-time upfront payment for each node you wish to reserve for a 1 or 3 year term. And as it's AWS managed, it offloads the management, monitoring, and operation of in-memory cache environments. And as I already told you, it provides support for two engines, Memcache and Redis. And for the GST and budget considering people, it provides detailed monitoring statistics for an engine node at no extra cost via Amazon CloudWatch. And Amazon Elasticache is available in all AWS regions and allows you to run your cache nodes in Amazon Private Cloud, that is a VPC. So that's one less thing to worry about, isn't it? So next off, let's check a very important concept about cache memory in terms of database. So to really understand the concept of caching and Elasticache and to really accept what the tools like Redis and Memcache have to offer, you really need to understand this simple but interesting concept, which is called cache hit and cache miss. So before moving into this, I want to ask you something. Like I told you that caching is faster, and yes, it uses the main memory, but why is it fast and why do you need caching? So when you have a pool of data or a set of data that you might need to retrieve very frequently, and the frequency at which it changes is low, then you are just going to access the same data repeatedly over a period of time, and it would be a headache if every time you try to make a request and try to get the data back, it takes a longer time. That would be a headache, isn't it? So I'll give you an example. You are going to an information center booth or an information booth, and there is a person who answers the most frequently asked questions. Like, hey, which screen is the movie playing right now? He would say A2. And there might be hundreds of people who might ask him the same question. And he might not think twice before giving you his answer. And that's fast, isn't it? And let's suppose you ask him the next time, like, what is the next change? What is the next change of the movie? He might not have the answer. He might just ask the movie theater manager to get your answer. And that might be more time consuming compared to the information he already had readily available to him. So that piece of readily available information is cache. And the time he went back to his manager is the stored data in the volume or the database. So as we know, there are levels at which data is written to the memory. So the first level being level 1, the register, L2, the second level, which is the cache, L3, the third level, which is the main memory, and the last one is the secondary memory, that is L4. There are other stages as well, but these are the most important ones. So remember one thing very carefully, that data is written to the cache and it's written one block at a time, and each block also has a tag that includes the location where the data was stored in the cache. So if you look at the example here, we have our user, we have our cache memory and the database. So cache hit means the data that you received was successfully returned from the cache memory. Okay, by not disturbing your database which would be a very costly operation. Okay, and cache miss happens when the data you want isn't found on the cache memory. In turn, has to be accessed from the database, and then it has to also be written onto the cache. So this is the primary difference between cache hit and cache miss. And if we turn the tables around and look at the Elasticache way, so just replace the cache and put your Elasticache in between, and that can be your Redis or Memcached, and it would work the same way as I explained just now. Smooth, isn't it? So you have the same principles here as well. It's just the replacement of the actual Elasticache. So let's see another use case for our solutions architect perspective. The most important, or you may say the most common use case that we have for any well-formed application is that the user always logs in to get access to the application. And to help the user not to flip out and make it very easy when he tries using the application again, the most widely used way is to store the user session data. So within the time limit, the user will exactly see what he wants as per his or her customization. So here is our user, and this is our application. And when the user logs in, we store the user data in Elasticache. Okay, and that is what we call our write session. And when the next request comes along, as we are using AWS and we are saints at designing applications, we use auto-scaling groups in place for high availability. The request may be served by some other instance of the application, and the beauty of this, or beauty of using session store, is that the app won't ask you to relog in again. It will straight away let you use the app as if nothing happened. And that's where we have our read sessions, where we get the same session back from Elasticache, and that would be pretty sick and pretty fast. Okay, so I hope you got an idea of what type of questions might be asked in the exam. Like, let's suppose you have your web application running with ASG and you have a database, and the user are having issues managing sessions and it's a bit slow, so you might prefer using Elasticache. Okay, so they may ask you like what type of service you want to use. That could be used here. So if the option is given as Elasticache, please choose that. So here we are going to discuss on how we should use Redis and Memcached, and it won't be asked as well. But you should remember that when you see Redis or Memcached or user session store, think Elasticache and make sure you read the questions thoroughly. Okay, so let's move on. So as I already told you, there are two offerings from Elasticache, Redis and Memcached. And let's see what is the difference between both of them with the perspective of Solutions Architect and AWS. So the first thing that you need to remember is that both of these databases are in-memory key value stores, like a key and a value. That's it. Pretty simple. That's why it is very efficient. So with Redis, you can keep your data on disk with a point-in-time snapshot, which can be used for archiving or recovery. But there are no snapshot provisions available for Memcached. And Redis gives you multi-easy replications. So Redis lets you create multiple replicas of a Redis primary. And this allows you to scale database reads and to have highly available clusters. So there are no replications for Memcached. So if you wish to have replications for your Elasticache, then you might use Redis. So Redis supports transactions that let you execute a group of commands as an isolated or atomic operation. But this feature is not available in Memcached. So Redis supports pub/sub messaging with pattern matching, which you can use for high performance chat rooms, real-time comment streaming, social media feeds, and server intercommunication. But there is no publisher or subscriber support of pattern matching in Memcached. And Redis allows you to execute transactional Lua scripts, but here on Memcached you won't find that. And there are no multi-threading for Redis, but Memcached is multi-threaded and it can make use of multi-processing cores. This means that you can handle more than one operation by scaling up compute capacity. Okay, so I hope this was clear, and these are the points that you need to remember. So let's move on. So the next thing on the line for us with respect to Elasticache is security and caching strategies. So with Redis, first thing you get is in-transit encryption, that is for TLS. So it's the encryption of data at transit that we already know. You enable in-transit encryption on a replication group by setting the parameter transit encryption enable to true. In CLI terms, you can term it as -transit -encryption -enable when you create the replication group. So next is for the data at-rest encryption in Elasticache for Redis. So it provides at-rest encryption using the AWS KMS key, and which can help you both for disk during sync, backup, and swap operations as well, and it will help you for your backup stored in AWS S3 as well. The last one that we have here is authenticating users with Redis Auth, and Redis authentication token enables Redis to require a token or a password before allowing clients to execute commands, thereby improving data security. You should remember this point because this came in the exam for Solutions Architect in March 2020. So the question was like, our users are using Redis and how will you improve security for login? So you might see the option of Redis Auth and you can go ahead and choose it. And moving on to the Memcached. Memcached uses SASL based security authentication. I hope you might be aware of simple authentication security layer, which unfortunately we won't be discussing in this session. So there are three caching strategies that we have for Elasticache, and they are, one is lazy loading, one is write through, and one is adding TTL. And this is what we are going to learn next. And this is really important, so please pay attention. So lazy loading, it's very important, so please pay attention to this. So lazy loading is a caching strategy that loads data into the cache only when necessary. So let's understand this with the visualization. But before that, I'll tell you something about Elasticache and lazy loading. So what happens is, so Amazon Elasticache is an in-memory key value store that sits between your application and the data store or the database that you have. So whenever your application requests data, it first makes the request to the Elasticache. And if the data exists in the cache and is current, Elasticache returns the data to your application. So if the data does not exist in the cache or it has expired, your application requests the data from your data store, or which is your database. We have our RDS databases and other databases, right? So a data store then returns the data of your application, and your application then next writes the data received from the store to the cache. And this way it can be more quickly retrieved the next time it is requested. Okay, so what happens here is, so we have the application here and the Amazon RDS database here, and we have Elasticache sitting in between. So what happens here is, first, the application will make a request, and if the requested data is available in the Elasticache, it will be sent back to the application itself. And then what happens in another case, what if you make a request and if it is not available, then it will be sent to the database for its retrieval. So what happens here is, if you are able to retrieve the data successfully from the cache, then it's a cache hit. And if you're not, then it's a cache miss. Okay, so this is basically the strategy of lazy loading. Here what happens is, the cache hit occurs when the data is in cache and isn't expired, and your application requests data from the cache, and the cache returns the data to the application. And the cache miss, as I told you, occurs when the data isn't in the cache or is expired, and the cache does not have the requested data, so it returns null. And your application requests and receives the data from the database. Okay, and then the application updates the cache for the new data. Okay, and this is the full cycle of what we call as our lazy loading, because most of the data is never requested, and lazy loading avoids filling up the cache with data that isn't requested. Okay, so I hope this was clear. Let's move on to the next one. So in write through, what happens, and the strategy what we have here is, it adds data or updates the data in the cache whenever data is written to the database. And because the data in the cache is updated every time it's written to the database, the data in the cache is always new, or the latest, or the current data. One more thing that happens here is that every write involves two operations. One, a write to the cache, and the next one, a write to the database. So which adds latency to the process. Okay, so that said, end users are generally more tolerant of latency when updating data than when we are retrieving data. Okay, so because you can spend more time when you're writing the data than while retrieving, because while retrieving the data, if it is slow, then you get more frustrated, isn't it? And there is an inherent sense that updates are more work, then thus take longer time, and this is a huge advantage on its own. So because as you think that while writing it takes an update operation and or a post operation, it takes more time, then you are psychologically prepared that yes, it's going to be taking a longer time, but while retrieving, you want the data to be fast. And the disadvantage here is, if you spin up a new node, whether due to node failure or scaling out, you might lose your data. until and unless it's added back. But this can be fixed if you use write through in conjunction with lazy loading. So if you have a lazy loading in place, then with write through you can have it. And another interesting thing is most data is never read, which is a waste of resources. By adding a time to live or TTL value, you can minimize wastage space or wasted space, so which we will discuss next. So by adding TTL or time to live, as the name suggests, how long you are going to live, and it's the amount of time that the data will prevail in the cache. So time to live or TTL is an integer value that specifies the number of seconds until the key expires. Okay, so Redis can specify seconds or milliseconds for this value. When an application attempts to read an expired value, it is treated as though the key was not found. Okay, the database is queried for the key and the cache is updated again. And this approach doesn't guarantee that a value isn't stale. However, it keeps the data from getting too stale and requires that value in the cache are occasionally refreshed from the database. So with TTL, you can get the best of both worlds, that is the lazy loading and write through. And this is the most sought after caching techniques. So I hope with this, you might have a strong understanding of how cache works and what we can do with it. And you should remember that when you see Redis, Memcached or user session store, think Elasticache. So let's talk databases. So everyone has used a database before, I hope, isn't it? And if you haven't, don't be taken back by this. I'm sorry if I'm digging into things too deep, but let's talk about this. So a database is a data structure that stores organized information. Let's suppose you have a phone book and you store names and numbers in your phone book, right? So if that is also a type of data that you store, and the place that you store it can either be a file or Excel sheet or a database. So in your phone database, once you have stored your contact information like name, number, email address, you will get the capability of either reading the contacts or editing or updating it, or if you wish to, then you can delete them as well. And these data are stored in as what we call as tables, isn't it? So the operations that we spoke about, these form the basic CRUD operations. And a database is an entity that has these abilities. So as I've already mentioned, the write, read, edit and delete, where write is basically your create operation, read is obviously your read operation, edit, that you edit the information that you have in hand, is called the update, and delete sounds similar to delete as well in the CRUD. So the basic CRUD operations form the four major pillars of the operations that we perform for a database. So create, read, update and delete. And the concept which is really important here is a relational database. So a relational database is a database based on the relational model of data. For example, if you're working in an organization and you want to store employee information, there can be multiple tables related to it. For example, let's suppose we have two tables, one for employee where we store the information like name and ID, and the other one that we have for the department and where we are storing like the ID and the department itself. Then we have a relation between both the tables, as we can see that the common entity that we have in both the tables is ID, which creates a relation between both the tables. And as we can say it rightly, a relational database is a type of database that stores and provides access to data points that are related to one another. Our data point here is ID. And in our relational database, we can deduce or read John with ID 123 is from physics department, because there is a relation between both the tables. So if you write a query based on this selection, then you can read the data as per your requirements. I hope this was a simple explanation of what database and relationship means. And generally, you might set up your database like MS SQL or Postgres or MySQL on a server or a local machine, and you need to install all the things that you need, isn't it? But what if I say there is a service which can take all the headache of setting things and managing the database from you and will help you run your database with ease? Yes, I am talking about Amazon RDS, or what we call Amazon's relational database service, and this is what we're going to discuss next. And welcome to RDS. And as I already told you, there is a service which can take all the headache of setting things and managing the database from you and will help you run your database with ease. Amazon Relational Database Service, or Amazon RDS, makes it easy to set up, operate, and scale a relational database over the cloud. And how does it help? It actually provides a cost-effective resizable capacity of database store while automating time-consuming administrative tasks such as hardware provisioning, database setup, patching, and backups. And Amazon RDS is available on several database instance types, which are both optimized for memory and performance or I/O. And as you can see here, I have listed out all the familiar database engines that AWS RDS provides support for, which includes Amazon Aurora, which is the Amazon's proprietary database, and PostgreSQL. You can use MySQL, MariaDB, Oracle, and Microsoft SQL Server as well. And you can use the AWS Database Migration Service to easily migrate or replicate your existing database to Amazon RDS as well. So this option is also available to you. So I hope this was clear. Let's move on. So there are ways we can make sure we have our database set up and make use of it on AWS, isn't it? We can easily install one of them on the EC2 instance and get a readily available AMI that can give us the setup itself, isn't it? But if everything was green on the manual side, what was the need of having a service which would do all that for us? That's why we need to look into the benefits of using RDS over the ways we can set up a database using EC2 or AMI that we call. So the first point that we have here is AWS Managed DB. And with RDS, there is no need for infrastructure provisioning and no need for installing and maintaining database software. All of the underlying infrastructure is handled by AWS itself. You don't need to be worried about the physical aspects of it, and you need to just focus on the data at hand and the way you use it. One thing that sets it apart from others is Amazon RDS database instances are pre-configured with parameters and that are set appropriately for the engine and class that you have selected, and you can launch a database instance and connect your application within minutes. Okay, so the second one that we have here is the ease of patching. So Amazon RDS will make sure that the relational database software that is powering your deployment stays up to date with the latest patches. That is basically your operating system patches, and you can exert operational control over when and if your database instance is patched. So you can as well tell AWS or schedule a maintenance window where you want to have your database patched. So you can tell Amazon or AWS that this is the time period that I want my maintenance window to be there, and this is the time when I want my database to be patched. So the third point that we have here is the monitoring database. And Amazon RDS provides Amazon CloudWatch metrics for your database instances at no additional charges, so that you can use a CloudWatch to monitor your events and logs to make better decisions. And Amazon RDS also provides enhanced monitoring, which provides access to over 50 CPU, memory, file system, and I/O metrics, or the disk I/O metrics, and performance insights. And it also provides an easy to use tool that helps you quickly detect performance problems, and it's very good with monitoring, and you need to remember this for exam point of view as well. And the fourth one that we have here is scalability, which is one of the most important aspects of using RDS. So with AWS or cloud, we know that the thing that we always need is scalability. And here as well, you can scale the compute and memory resources powering your deployment up or down, up to a maximum of 32 vCPUs and 244 GB of RAM. So if you're using Amazon Aurora, the Amazon Aurora engine is or will automatically grow the size of your database volume as your database storage needs grow, and up to a maximum of 64 terabytes or a maximum that you can define. And the MySQL, MariaDB, Oracle, and PostgreSQL engines allow you to scale up to 32 TB of storage, and SQL Server supports up to 16 TB. And this is something that you need to remember. And storage scaling is on the fly with zero downtime, and that's awesome, isn't it? So there is one more thing that we will discuss in length is read replicas. So read replicas in RDS makes it easy to elastically scale out beyond the capacity constraint of a single database instance for read heavy database workloads. You can create one or more replicas of the given source DB instance and serve high volume application read traffic from multiple copies of your data, thereby increasing aggregate read throughput. And read replicas are available in Amazon RDS for MySQL, MariaDB, PostgreSQL, and Oracle, as well as the Amazon Aurora DB that we have. And the fifth point that we have here is security, and AWS RDS provides encryption at rest and in transit. And RDS allows you to encrypt your databases using keys you manage through AWS Key Management Service, that is a KMS. On a database instance running with Amazon RDS encryption, data stored at rest in the underlying storage is encrypted. as are its automated backups, replicas, and the snapshots. And Amazon RDS supports transparent data encryption, that is the TDE, in SQL Server and Oracle for read. And Amazon RDS supports use of SSL to ensure there is a secure data, or to ensure security of data in transit. So for the security of data at rest, you can always use the AWS Keys Management Service, that's a KMS, to encrypt the data that you have. And for security of data in transit, remember that you can use SSL. And with RDS, let's suppose you are working with a private firm and that you want to have a database enclosed. And then AWS recommends that you run your database instance in the Amazon VPC, which allows you to isolate your database in your own virtual network and connect to your on-premise IT infrastructure using industry standard encrypted IPsec VPNs. Okay, so you can configure firewall settings and control network access to your database instances as well. So if you wish to, you can do that as well. And cherry on top is basically the resource level permissions. So Amazon RDS is integrated with AWS Identity and Access Management, that's the IAM, and provides you the ability to control the actions that your AWS IAM users and groups can take on the specific Amazon RDS resources. So which could be your database instance, snapshot parameter groups, and option. So let's suppose you are a developer and you don't have access to the production system, then you can tag the resource with either developer or production based on whom you want to provide the access. So you can tag the resources either with developer or production, and then you can tag them or attach them to the particular user that you have so that they have access to one of those on the basis of the role that they play in the organization. And the sixth one that we have here is a hardware upgrade. So as RDS is AWS managed, and Amazon RDS will automatically replace the compute instance powering your deployment in the event of a hardware failure. So one less thing to worry about. That's great. So next thing that we have is probably one of the most important things, is probably the most important one for the mission critical production systems. That's the disaster recovery. So with the multi-AZ deployment option that AWS RDS provides, you can run mission critical workloads with high availability and built-in automated failovers from your primary databases to a synchronously replicated secondary database. Okay, in this way, you can secure from those laps that might happen when there is a failure. As with all Amazon Web Services that we have seen, there are no upfront investments required, and you pay only for the resources that you use. And the last thing that we have here for performance, I hope you remember the point we discussed about the storage classes with respect to the volumes. Here as well, RDS provides general purpose SSD storage and provisioned IOPS storage with GP2. As we know, Amazon RDS general purpose storage is an SSD backed storage option, and it delivers a consistent baseline of 3 IOPS per provisioned GB and provides the ability to burst up to 3000 IOPS above the baseline. And when we talk about the provisioned IOPS, so the Amazon RDS provisioned IOPS storage is an SSD backed storage option designed to deliver fast, predictable, and consistent IO performance. So that's all we have for the benefits of using RDS over EC2 deployed database. So I hope that was clear. Let's move on. So the next thing that we have here is what is Amazon RDS read replication. So as we've already spoken in brief about read replicas, please focus on the next few minutes, as this is a very important concept that RDS provides, and as a solution architect, you would need to have a proper understanding of it. Okay, so read replicas in RDS make it easy to elastically scale out beyond the capacity constraints of a single database instance for read-heavy database workloads. So you can create one or more replicas of a given source DB instance and serve high volume application read traffic from multiple copies of your data, thereby increasing aggregate read throughput. So in simple terms, what it means is you can reduce the load on your source DB instance, that is your primary database, by routing read queries from your application to the read replica. Like let's suppose we have in our example here, let's suppose this is our application server, which let's assume is a very popular one. For the purpose of storing our data and reading or writing data, we have set up our RDS database, which can also be called as a primary database. Here on our main primary DB instance, we make use of it for read and write. Okay, so let's suppose we have another part of our application which needs a huge amount of read operations. I hope you remember in a database we can perform CRUD operations, and select is the operation or query that we use for reading the data from the database. So imagine your application actually needs a lot of read operations, Then to cope up with increasing demand, we can as well create a read replica that can be used for our application's read operations, and in a way decreasing the load from the primary instance. That's the beauty of using RDS, and yes, it's very convenient as well. And you might think, how does the read replica get the data to be read? So this is an asynchronous replication mechanism that lets data from the primary to be replicated across the read replicas. And if you think, bas itna hi, then read replicas can also be promoted when needed to become a standalone DB instance. So that is not dependent on the primary database replication to get the data. And one more thing that is really important for the exam, and you need to remember this, is you cannot have more than 5 read replicas, and Amazon only allows you to create up to 5 read replicas and need to be launched, and they actually have to be launched one by one. So in the example, if you can see, we have our main application which has the primary RDS database instance, and it works fine with read and write here, and that's the read and write operation we have. But when it comes to our reporting server, which has a huge load of read operations, we have created our read replicas so that we don't overload our primary database instance. And one thing is that with asynchronous replication, there might be a slight delay in the data to be replicated across your DB instance. But this is simple, isn't it? As a solutions architect, knowledge is one thing to have, but on the same lines, you should be able to think of options that get or yield you optimal performance. And that comes along with having a proper thinking and a bit of common sense, isn't it? So I hope that was good. Let's move on. So let's go over and let's discuss some of the important points that we need to remember for read replicas. So the first point that we have here is main purpose is scalability. As you know, that scalability is one of the major impacts that the read replicas provide us. And there is basically the use of asynchronous replication, where the data will eventually get replicated across the instance that you have or the read replica that you have in a short time. And all read replicas are accessible but can be used for read scaling. Okay, and no backup is configured by default. We will discuss on how to create the backup in a short while. So you cannot have any backups that are configured by default. So you have to manually configure them. And it can be within an availability zone, cross availability zone, or cross region. So you can have availability zone. So you can have read replicas across availability zones and across cross regions as well, or different regions as well. And for non-Aurora databases, the database engine upgrade is independent from the source instance, and for all Aurora databases, it is updated together. So the read replicas can be manually promoted to a standalone database instance, as I already told you, for the non-Aurora one, or to be the primary instance in case you're using Aurora. Okay, so if suppose in the exam it comes like which can be promoted to a standalone database instance and which one cannot be, or which one can be promoted to a primary instance, you must remember that the standalone database instance or the promotion to a standalone database instance is for the non-Aurora databases, and the one that can be promoted to a primary instance is basically your Aurora database or the Aurora RDS database. Okay, let's move on. Okay, just now we had a discussion about the read replication on single channel, and let's suppose our database instance crashes or the server gets destroyed. We must have something that can help us save our critical application so that it has a high availability and high uptime. So AWS RDS provides you read replicas, and with that it also provides multi-AZ read replicas. Yes, you can create or set your read replicas across availability zones. Amazon RDS multi-AZ deployments provide enhanced ability and durability for RDS database instances, making them a natural fit for production database workloads. When you provision a multi-AZ DB instance, Amazon RDS automatically creates a primary database and synchronously replicates the data to a standby instance in a different availability zone. Okay, so the benefit you get is each availability zone runs on its own physically distinct independent hardware and is engineered to be highly reliable. And in case of an infrastructure failure, the Amazon RDS performs an automatic failover to the standby or to the replica, the read replica that we have. And one of the beautiful things that we have here is, since the endpoint of your database remains the same after the failover, your application can resume database operation without the need for manual administrative intervention. So let's suppose there was a DB instance and it failed over, and along with that the URL or the endpoint got changed. Then you have to manually configure the database again, or the configuration files that you have again for all the properties that you have mentioned in the instances that are particularly accessing it. So basically, this is one of the very good features that we have, that the DB instance remains the same, or the endpoint for your DB instance remains the same after the failover, so that your application can resume database operations without any external modification. So here, if we see visually, we get the understanding that our application server uses our AWS RDS instance, and which is in our AP South 1A availability zone, and our read replica is in AP South 1B. And they are connected or replicated using a synchronous approach of read replication. And if you can see, there is a DNS auto failover condition set, and then at the failover point, it will read from the standby node that is in the other read replica. So let's see what conditions can provoke the failover and what can be done about it. So what I'm going to say here is really important. Listen to this very carefully. On instance failover or instance failure in Amazon Aurora deployments, Amazon RDS uses RDS multi-AZ technology to automate failover to one of up to 15 Amazon Aurora replicas you have created in any of the 3 availability zones. If no Amazon Aurora replicas have been provisioned, in the case of failure, Amazon RDS will attempt to create a new Amazon Aurora DB instance for you automatically. Here, if you assume that there was an issue and our database instance got crashed, then upon a failover, RDS will automatically launch a DB instance for you. When we try and understand it visually, what happens here is, if you can see, we have our application in at AP South 1A AZ, and there was a failover. And how does RDS know that there is a failover? So DB instance failover is fully automatic and requires no administrative intervention, and Amazon RDS monitors the health of your primary and the standbys and initiates a failover automatically in response to a variety of failure conditions that are set. Okay, so you need to understand that when you have your multi-AZ read replica, you set your read replicas in place. And when it fails, as you can see, it will switch to the second instance in another availability zone, that is our AP South 1B, which becomes our primary RDS, and will point to the standby instance as its read replica. So Amazon automatically performs a failover in the event of any one of the following cases that we have. The first point is loss of availability in the primary availability zone. So that if the primary availability zone gets obstructed or it's no longer connected, then it is one of the conditions for a failover. And the second point that we have is loss of network connectivity to the primary. As I already told you, if there is any problem with the network or anything that is not able to connect to the primary, then it will automatically fail over. And the third point that we have is compute unit failure on primary. And the fourth one, the storage failure. Let's suppose there is no storage capacity left, it will try to fail over. And when operations such as DB instance scaling or system upgrades like OS patching are initiated for multi-AZ deployments, listen to this carefully. For enhanced availability, they are first applied on the standby prior to an automatic failure. So they are first applied to the standby, then to the primary one. So this is really important because the exam can trick you into asking questions like on which one actually it does apply first. So you have to remember that the OS patching and the system upgrades are applied to the standby prior to doing it on the primary one. Okay, I hope it was clear. Let's move on. So let's discuss a few points on the RDS backups and restore. We will cover this quickly. This is also very important. Okay, so the first thing that I want to tell you, or that's already highlighted, is by default, Amazon RDS creates and saves automated backups of your DB instances securely in Amazon S3 for a user specified retention period. Okay, don't worry about this. We will be seeing all the options that we have here in the demo that we are going to have a very short while. So let's move on then. So the first thing that we have here is automated backups. It's turned on by default. The automated backup feature of Amazon RDS will back up your databases and transaction logs, and Amazon RDS automatically creates a storage volume snapshot of your database instance, backing up the entire DB instance and not just individual databases. So this backup occurs during a daily user configurable 30-minute period window known as the backup window, and automated backups are kept for a configurable number of days called the backup retention period. And your automatic backup retention period can be configured up to 35 days. So it ranges from 1 day to 35 days. So manually the default is basically like 7 days, and you can switch it up to 35 days as well. And the second point that we have here is point-in-time restores. You can point your database instance to any specific time during the backup retention period, creating a new database instance. To restore your database instance, you can use the AWS console or command line interface. To determine the latest restorable time for a database instance, use the AWS console or command line interface to look at the value returned in the last restorable time field of the database, for the database actually. So the latest restorable time for a database instance is typically within 5 minutes of the current time. So mostly you will be able to access it using the variable that we have specified. And the next point that we have here is the database snapshot. So the database snapshots are user initiated backups of your instance stored in the Amazon S3 that are kept until you explicitly delete them. And you can create a new instance from the database snapshots whenever you desire. Although database snapshots serve operationally as full backups, you are built only for the incremental storage use. That's very good. Okay, let's jump on to the next one, the snapshot copies. Okay, with Amazon RDS, you can copy DB snapshots and DB cluster snapshots. You can copy automated or manual snapshots as well. So after you copy a snapshot, the copy is a manual snapshot itself, and you can copy a snapshot within the same AWS region, and you can copy a snapshot across AWS regions, and you can as well copy a snapshot across AWS accounts. Okay. And snapshot sharing, that's the next point that we are going to discuss, is using Amazon RDS, you can share a manual DB snapshot or DB cluster snapshot with other AWS accounts. So sharing a manual database snapshot or a database cluster snapshot, whether encrypted or unencrypted, enables authorized AWS accounts to copy the snapshot. So sharing an unencrypted manual database snapshot enables authorized AWS accounts to directly restore a DB instance from the snapshot instead of taking a copy of it and restoring it from that. This isn't supported for encrypted manual DB snapshots. One thing that we need to also remember is sharing a manual database cluster snapshot, whether encrypted or unencrypted, enables authorized AWS accounts to directly restore a database cluster from the snapshots instead of taking a copy of it and restoring it from that. So if you have authority or you have authorized an AWS account to basically create a snapshot from the manual snapshot that you already have shared, they don't have to take a copy of it and restore it from it. They can do it directly. So now let's discuss Amazon RDS encryption of data at rest. Okay, the first thing you must understand is that this will surely come in the exam, and I have faced questions from this topic. Understand this very carefully. Okay, so the Amazon RDS encrypts your database using keys you manage with the AWS Key Management Service, or the KMS. I hope you remember KMS, which is used to maintain the secure encryption keys that we use for our services. We use the same keys to encrypt the database. On a database instance running with Amazon RDS encryption, data stored at rest in the underlying storage is encrypted, and are its automated backups, read replicas, and snapshots. And RDS encryption uses the industry standard AES 256 encryption algorithm to encrypt your data on the server that hosts your RDS instance. If you see the example visually here, the customer has the keys generated and it's the master key, and each of the data at rest is being encrypted using the unique key that is generated based on the master key. So I'll reiterate this once again. If you see, the customer has the keys generated and its master key, and each of the data at rest is being encrypted using the unique key that is generated based on the master key. Okay, so basically you use the data keys to encrypt the data which is encrypted by its own master key, and this is quite a bit confusing, isn't it? And the third step that we have is we use the data keys to encrypt the data that we have on the database instance. Okay, so what exactly happened here is we have the customer master keys, and from that master key we encrypt the data keys, and that data key is used to basically encrypt the customer data in the RDS instance. Okay, so the first three steps that you see here, the three steps. The first step, again I want to reiterate, you create the master keys, okay, the customer keys based on the master keys that you have, and from that you encrypt the data keys, and that data key is used to encrypt the customer data. Amazon RDS also supports transparent data encryption, or the TDE, if you're using SQL Server or Oracle. So you might ask, what is TDE? So TDE basically is transparent data encryption. It is basically a technology employed by Microsoft, IBM, and Oracle to encrypt database files. Okay, so TDE offers encryption at file level, And TDE solves the problem of protecting data at rest, encrypting database both on the hard drive and consequently on the backup media. It does not protect data in transit. And one of the most important things that you need to remember about TDE is it is not used for data or protection of data in transit or the data that is currently in use. Okay, it is always used for the data at rest. So as we have discussed data at rest or the encryption of data at rest, let's go to the interesting one. So data in motion is often considered less secure, and its vulnerability makes it a cup of tea for hackers. If you are unsure or have only heard the term, then it's basically data traveling from network to network or data transfer from local storage to cloud storage. So in simple terms, it's basically the data that is currently in use. So for this type of data at transit, RDS provides a mechanism that encrypts communication between your application and your DB instance using SSL or TLS. Okay. And Amazon RDS creates an SSL certificate and installs the certificate on the DB instance when the instance is provisioned so that your data is secure during transit. And you can as well configure this in your clients or the SQL clients that you have. So for MySQL clients, you launch the MySQL client using the --SSL_CA parameter to reference the public key in order to encrypt your connection. And there is a query that I have already mentioned, grant usage on *to user@required SSL. So you can use this query to basically have your SSL encryption in place for the data in transit. And for SQL Server that you have, you can download the public key and import the certificate into your Windows operating system. And by this, you can as well encrypt the data at transit. Oracle actually uses the Oracle native network encryption with a DB instance. And you can also require your database instance to only accept encrypted connections. So if you're using Oracle by default comes with a native network encryption when you have the database instance in place. For Postgres, you can use the command that we have here is the parameter that you have, or the configuration that you have is rds.force_SSL equals 1 in the RDS console. And you can set this parameter so that your data is secure or the data is encrypted during transit. So one of the major important points when we discuss about security is access control. And this is one of the new features that we have for Amazon or the AWS services that we have. So Amazon RDS is integrated with AWS Identity and Access Management, that's the IAM, and provides you the ability to control the action that your AWS IAM users and groups can take on the specific resources. So that can be your DB instance, your DB snapshots, your DB parameter groups, or DB event subscriptions, or the DB option groups. And you can also tag your Amazon resources or the Amazon RDS resources and control the action that your IAM user or group can take on the groups of resources that have the same tags and associated value. For example, you can configure your IAM rule to ensure that developers are able to modify development database instances, but only database administrators can make changes to the production database. And let's see this visual example here. When you first create a DB instance with Amazon RDS, you will create a master user account, which is used only within the context of Amazon RDS to control access to your database instances. So the master user account is a native database user account that allows you to log into your database instance with all the database privileges. And you can specify the master username and password you want associated with each database instance when you create the database instance itself. And once you have created your database instance, you can connect to the database using the master user credential. Subsequently, what you can do is you can create the additional user accounts so that you can restrict who can access your database instances. So the first thing that obviously I suggest you to do is create the admin, and then once you have the login in place, then create the user groups or add the users and provide the tags so that you can assign the users to the tags that belong to that production or the development environment or the database instance that you have. Okay, so that you can have restrictions in place. Otherwise, what will happen is if suppose the developer is testing out some of the resources or some of the queries that they have and it goes accidentally to the production environment, then it might be a huge problem or loss of data that can happen in your application. So the database instances deployed within an Amazon VPC can be accessed from the internet. Yes, it can be accessed from the internet or from Amazon EC2 instances outside the VPC via VPN or bastion hosts. that can launch in your public subnet. So if suppose you have your Amazon VPC and you want to have public access, and if you want to have internet access to the database or the Amazon EC2 instances that you have, you want them to be able to access the DB instance, then you can use it, and you can use the VPN or the Bastion hosts that you can launch it in your public subnet, and they can make use of it. And to use a Bastion host, you will need to set up a public subnet with the EC2 instance that acts as a SSH Bastion. So this public subnet must have an internet gateway and routing rules that allow traffic to be directed via the SSH host, which must then forward requests to the private address or the private IP address of your Amazon RDS database instance. It's not that, clear, but as we discuss along with the lines of VPCs and how we create the public and private subnets, this will be more clear. So AWS RDS proxy is something that's fairly new, and it's still in the beta stage or preview state that you might say, but we need to discuss this anyway. So Amazon RDS proxy is a fully managed, highly available database proxy for Amazon Relational Database Service, or RDS, that makes applications more scalable, more resilient to database failures, and more secure. Okay, if you're confused about what a database proxy is, don't worry. It's like within a context of databases, a proxy sits in the middle between the application and the database. Okay, so it sits between the application and the database, and the application connects to the proxy, which forwards connections to the database. Okay, so as we are tech freaks, and the database we set up today in today's time can have a large number of open connections to the database servers, and may open and close database connections at a high rate, exhausting the database memory and compute resources, Amazon RDS proxy allows applications to pool and share connections established with the database, and thus improving database efficiency and application scalability. And with RDS, or with the RDS proxy, failover times for Aurora and RDS databases have reduced by up to 66%, and database credential, authentication, and access can be managed through the integration with AWS Secrets Manager and AWS Identity and Access Management. So you can have RDS proxy integrated with the AWS Secret Management and the AWS Identity and Access Management to make sure that you have your database credential, authentication, and access in check. And the way it works is same way as I explained before about proxy databases. So here as well, the Amazon RDS proxy sits between your application and your relational database to efficiently manage connections to the database and improve the scalability of your application. So yes, we have the RDS proxy, but what can it help us with? So the Amazon RDS proxy instance maintains a pool of established connections to your RDS database instances, reducing the stress on database compute and memory resources that typically occurs when new connections are established. Amazon RDS proxy is highly available and deployed over multiple availability zones, and in turn what it does is it increases application availability and reduces database failover times. And with the security, it manages applications data security with database access controls. Okay, this was quite informative. Let's move on. So these are some of the points that we need to discuss about the exam point of view for solutions architect. So let's go over them one by one. So the read replicas are used for select statements of SQL and not other statements in the CRUD operations. So you have to remember that select is basically read. So when you talk about reading or read operations in CRUD or the database, that means that the operation that is going to be performed is select. Okay, and insert, delete, and update are other operations which are basically, you can say it is a write operation in the sense of reading and writing. So where select is read and the other things are write. Okay, and Amazon RDS also supports transparent data encryption for SQL Server and Oracle, and transparent data encryption can be used on top of KMS. And once you use this, you must understand that there can be an impact on the performance as well. So make sure you use them wisely. And Amazon RDS encryption uses the industry standard AES 256 encryption algorithm, okay, which is very secure. And Amazon RDS is integrated with AWS Identity and Access Management and provides you the ability to control the action that your AWS IAM users and groups can perform. And the lifespan of an authentication token that you have here is of 15 minutes that you must remember, and SSL must be used while connecting to the database. Hello everyone, and welcome back to the AWS RDS demo. I hope you have already seen the tutorial that we had for Amazon AWS RDS. And if you haven't, then please go and watch that before coming on to the demo. Or if you just want to watch the demo, then you can proceed further with this video. And that's it. Let's start with the demo then. So this is the management console that we have for AWS. So here you need to just find RDS, and you can just go ahead and click on this one. And once you have clicked on this, we will get the page for the RDS to create our RDS database. So here you can see the options that we have for Amazon Aurora as well to create the Amazon Aurora database. And here the create database option that you see here, this is for the RDS database. So if you wish to create the Amazon Aurora database, you can click here and go ahead with this. For now, what we are going to do is we are going to create the RDS database. So we will click on this option. And as you can see here, the service health that you have, the Amazon Relational Database Service for Mumbai, its service is operating normally. So it's a good sign for us because we are going to create a database. If it was unhealthy, then we will not be able to create the database for now. So this is a good thing. So we'll just click on create database. So once you've clicked on create database, you will get two options. So choose the database creation method. So here there are two options that are available to us. The first one is the standard create, and the easy create is the second option that we have. So for the standard create, it gives us the flexibility to customize the database creation process as per our demands. So you set all of the configuration options, including ones for availability, security, backups, and maintenance. And for the easy create, it's like a easy setup that we have for the installation process for any of the software that we used to have, like in Windows or Mac. So it'll just go ahead and do the best practice and configuration that we have, and it'll create the database for us. So use recommended best practice configurations. Some configuration option can be changed after the database is created. So we want to see all the options that we have for creating the RDS database. So we will choose standard create, and the second option that you have here, the engine option. So engine options are basically the sought after database engines that we have, like the Amazon Aurora. This is the new one that Amazon provides, the MySQL and the MariaDB, PostgreSQL, Oracle, and the Microsoft SQL Server. So based on your requirement, you can go ahead and create a Postgres or a MySQL or a MariaDB or a Oracle or a Microsoft SQL Server database. And for today's demo, we will be going with Postgres, and this is the current version that we want. And one more thing that you need to remember is Amazon Aurora is not included in the free tier, and apart from that, you can create any other database that you want. Okay, so if you want to create PostgreSQL 12 in the preview environment, click here, but I want to just use this version for now. And there are templates also you can choose. Like, let's suppose you're working in a production environment or a dev instance, then you can choose one of these templates, but we are a bit low on budget, so we'll go with the free tier one. So I'll click on free tier, but remember that you have all these options in place when you're working for your organization and your organization wants to have a database for the production environment or the dev instance. You can choose one of them as a primary template that you have. Okay, so the free tier, actually use RDS free tier to develop new application, test existing applications, or gain hands-on experience with Amazon RDS. So that's what we want to do, and that's the best option that we have here, the free tier. So we have selected this. So moving on, the settings, we can provide a name for the database that we have, the DB instance identifier. So what I'm going to do, I'm going to name it my Postgres DB, and the master username that I want to set is admin, and I don't want to generate a password automatically, so I would not select this option of auto generate a password. I will just give something like a simple one. Okay, so I've given the password. You can also choose one of the passwords that you like, and you can give it as well. So the next thing that you have here, the DB instance size. So choose a DB instance class that meets your processing power and memory requirements. The DB instance class options below are limited to those supported by the engine that you selected above. Okay, so based on the engine type that you have selected, like it might be Postgres or MySQL or MariaDB, you get to choose one of these. And you can see these options like standard class and memory optimized classes have been grayed out. This is because you have chose a free tier option for creating the database. So if you choose production or dev instance, then you might as well go ahead with these two options. So you will get these two options will be enabled for you. So the burstable class, this is the only class that I have for now. If I click on this drop down, this is the only option that is available. So db.t2.micro is the only thing that is available for us in the free tier, and we are restricted to this. So we will go ahead and choose this. But if suppose I want to reiterate this once again. So let's suppose you have a production environment template or a database or is a dev instance template, then you can go ahead and choose one of these. Okay, based on your requirement. So now we will go ahead and select db.t2.micro. Next one that we have here is the storage. So you can select a storage type. So with here you get the two options that we have already discussed, like RDS provides two storage type options. That is, one is the general purpose SSD and the provisioned IOPS SSD. So now we can just go ahead and select the general purpose SSD for now, and the minimum and storage capacity that you can allocate is 20 GB. So we have allocated 20 GB, and that should be fine for us for the demo, and the maximum is 16384 GB. Storage auto scaling provides dynamic scaling support for your database storage based on your application needs. So I don't want to have a storage auto scaling feature enabled for myself, so I'll not select this. So if you go ahead and select this, you can choose like what the maximum threshold is, like what is the maximum threshold it should reach, and based on that you can basically choose to have a scaling for yourself, but I'm not going to do that. So once I've deselected this, the options disappear. For the free tier, we will not get the multi-AZ deployment. I hope you remember the usage and the benefits of having a multi-AZ deployment for your Amazon AWS RDS. For free tier, we will not get this option. And the connectivity. So either you can connect it to the virtual private cloud that you have to make it like secluded to your virtual private cloud, and either you can create a VPC, but I'll use the same default VPC that I have been using since the start. And there is one more thing, the additional connectivity configuration, where you have a subnet group that you can choose by default. And there is one thing that you need to remember, that we need to access our database publicly, or we want to have a public access for the database, so that we can connect to the database and we can use it. So what we're going to do, we are going to select the yes option here so that we can connect to our database from our local machine. I will just move forward with this. So VPC security groups is something that is very important for us. I would want to create a new VPC security group. So I will name it my Postgres-SG. So I'll name it as my Postgres-SG, and availability zone, I don't have any preference, but I can either choose it to be in AP South 1A or South 1B. And the database port that you have is by default 5432, and anybody who has already used Postgres would already know that the default port for Postgres is 5432. So that's fine for us. There are three options available for us: the database authentication. So the first option is password based authentication that we have already provided, like the password and the username that I gave. And you can as well connect it via the IAM database authentication, where you have provided access to this database to some of the IAM users. And based on that, you can also have access to this database. And password and Kerberos authentication. So choose a directory in which you want to allow authorized users to access or authenticate with this database instance using Kerberos. You can do this as well. But for now, we are going to move forward with password authentication. And the additional configuration that we have here is the database option, the initial database name that we want. So let's suppose you want to create a database by default. Once the RDS database spins off, you can just give it a database name for yourself. So I'll give like Demo DB. So Demo database is the name of the database that will spin up after the RDS database has been configured. So this is fine for us. So the DB parameter group that I have is default Postgres 11. So this is by default. I am not going to change it. And backups. So create a point in time snapshot of your backup, and you can enable automatic backup, and there's a backup retention as well. And the backup retention period is like the number of days that you want your backups to be retained. So this is configured to 7 days, and you can go up to 35 days as well. So after that, there are options available for us to create a backup window. Like there is no preference, means it will do it automatically, or you can select a particular window between what time period you want and what is the duration for the time that you have, and copy tags. So snapshot option will be available to us, but I will not have a select window option selected, so I'll go with the no preference one. So the default retention period of your performance insight is also 7 days. That can be increased to a long-term retention period of 2 years. So this is also a very good option that we have. The master key, the default AWS RDS key that I have, that I can use it, or I can enter a ARN, but I don't have a ARN right now, so I'll just click on this one. So what it says here is you cannot change the master KMS key after your performance insights have been enabled. This is something pretty much that we must be aware of. And monitoring, I don't want to enable any monitoring right now, or log export for any of those PostgreSQL or upgrade logs. So if you have a CloudWatch monitoring in place, then you can assign an IAM role to it so that it can be pushed, or the logs can be published to that CloudWatch log feature that we don't have here. And maintenance, enable auto minor version upgrades. So this is one of the best features that you are going to get with RDS, because it is auto managed, or it is managed by AWS itself. So once you click on this enable auto minor upgrade, this will be automatically upgraded. So you can select for this maintenance window also, you can select a window in which you want to do the maintenance. Otherwise, if you click on no preference, it will do it as per the recommended AWS maintenance upgrades. So it will do it in that way. And so this is one of the best features that we have, because we don't want to have the headache of updating our infrastructure, and as this is AWS managed, and they will be doing it for us. And the next option that we have here is deletion protection. So if you click on this or select this option, the enable delete protection, so what happens is it protects the database from being deleted accidentally. While the option is enabled, you cannot delete the database. So I can choose this, not a problem. So I can have this enabled. So the monthly estimated cost that we have here, the estimated monthly cost that Amazon provides us is like the AWS RDS tier is available to you for 12 months, and each calendar month the free tier will allow you to use the Amazon RDS resource list. So it's like 750 hours of Amazon RDS in single AZ db.t2.micro instance that we chose, and 20 GB of general purpose SSD, that is the general purpose storage. So we have used that as well, and 20 GB of automated backup storage for any user initiated DB snapshot. So you can use these options in the free tier, and if you exceed any of these, then you will be charged. So don't worry about this right now. If you don't want to spend money on this, you can just watch the tutorial so that you get the information without spending the money. And that's how YouTube works, right? So yeah, it's good. Just go ahead and click on create database. Okay, so this is one more thing. You cannot provide a master username as admin because it is a reserved keyword. So this is something that good that we got to know here. So I'll change it. I'll make it Pythoholic. Okay, so I think this should work. So now that everything is done, you can just go ahead and create database. Let's wait for it. It might take some time. So as you can see, it's already written that your database might take a few minutes to launch. So we can wait for that, and you can also grab some coffee or tea. Meanwhile, your database will be ready. I'll wait for the time and I'll come back again. So now as you can see, the status has changed from creating to backing up, and the CPU percentage also has been shown here, and we'll wait for some more time. So now Postgres instance or the RDS instance is available to us. That's a very good thing. Congratulations on your first RDS database. So once you have created your database, you can just click on this one. Okay. And before that, I just want to go back and I want to check all the identifiers that we already have here. So this is the DB identifier that we gave, like my Postgres DB. There's the name that I gave, and the role is the instance. Engine type is PostgreSQL, and it is currently placed in AP South 1B. And the size of the database that you have, the instance size is db.t2.micro. That is the that is the one that is available to us in the free tier one, and the status fortunately is available right now. So the current CPU utilization is at 7.67%. The current activity has 0 sessions. Maintenance is none. The VPC, that is the default VPC that we have, and multi-AZ as we can't have multi-AZ in free tier. That will be no here. So you can go ahead and click on this one. And it is one thing to create a database or create a RDS database, and the important thing after this is to connect to that endpoint and make use of it, isn't it? So connectivity and security that you see here, the endpoint or the port that you have here is this is the endpoint that you want to connect. So let's suppose you have created your database locally, then you might use 127.0.0.1 and you connect it to 5432, isn't it? Or a local host, then 5432. Or if you have it any in a server, then you use that IP address of the server and connect to that particular port to access the database. Here we have got the endpoint URL for us. So this is pretty much it. And what we are going to do is we are going to just go ahead and copy this, and we'll go back to the PG admin, and these are servers that you see here, right? Server option. So here, once you are in PG admin, what you're going to do is you're going to right click on this and create a server. And basically what we need is we want to give it a name for the server that we have created here. So this is basically to have an interaction point in PG admin for our database that we have created, or the RDS database that we have created. So you can give it any name. There's no constraint on whatever name that you have given for the RDS database. You can name it anything that you want for your own identification. So I will give it like my RDS database. The next thing that I want is to add the connection details here. Paste the host name that I already had. The maintenance database, I hope you remember the database name that you gave. So I gave it Dynamo DB, and the username was Pythoholic, and the password was sorry. So I can just go ahead and save this password as well. And if there are any SL configuration that you have configured for the database, you can use it. Or if you are connecting it through the SH tunnel or a Bastion host or jump server, that you can provide this information here. And the advanced options also are available to you. And this is pretty much a very good tool. Like PG admin gives you a lot of options to connect to your Postgres instance. And once you have configured all these operations or the options that you have, then you can just go ahead and click on save. So once you have clicked on save, that's it. It'll give you all the options now. So now we have our Dynamo DB in place right now. And that's it. We have connected to the database instance that we have for RDS. And one more important thing that you need to remember is like once you click on this option that you have and go to actions, there you see all the options that are available to you that you can perform on the database that you have created, the AWS RDS database that you have created. So either you can stop it, you can reboot it, you can delete it, you can create read replica. So I hope you remember the tutorial that we had for AWS RDS where we discussed in length about the read replicas. So you can create read replicas as well from here, take a snapshot and restore it to the point in time that you had created the snapshot. So this is pretty much everything that the options that are available to you for AWS RDS database. Let's move on. And feel free to create your own RDS database in the free tier account. And it's pretty simple, and you can learn a lot of things from there itself. So if you have any doubts related to this, or if you have any errors that you're getting on this creation process, then please put that in the comments, and we can discuss in our one-on-one session that we are planning to have. So I'm going to have a one-on-one session on Saturdays or probably weekends, so that we can sort out all the errors that you're getting, or if you have any questions that you want, you can put it across in the comments list as well, so that we can sort it out. So this was something that I really wanted to share with you guys. So if you liked, please share and subscribe, and that's it. Have a good day. Thank you. Bye-bye.
So that's all from my side today, and if you're new here, then please do subscribe. If you wish to buy me a coffee, then you can do that as well. The link is given in the description below. So until next time, stay safe, stay healthy. It's Pythoholic signing off.